My name is Andreas Reuter. I am the director of Fraunhofer IWIS, as you might guess, with the logo in the background and so on. I have the pleasure to welcome you to the third edition of our conference, Virtual Wind Today. The conference has evolved over the last months as a consequence of the limitations due to the COVID crisis. As you're all aware, everybody is going virtual. We did it as well. But it's also a result of our good cooperation between European research centers, in this case between Eurecatapult and us. And we're working on this one since a couple of years, coordinating our activities and looking for opportunities to do things jointly, exchange experience and so on. And so this conference is also a format to give this a basis. And we're looking forward to continue this. Of course, we have a couple of challenges facing us, especially the Brexit coming up, but I'm very confident that we can continue our good cooperation in spite of that. And Andrew, if not, I'm going to send you a postcard once in a while, and then we see what we can do with that. No, we stop kidding here. Today it's about offshore wind, and also it's currently not really in the focus of public discussions. Climate change and the need for an energy transition is, of course, highly important and remains highly important. And therefore, this is also our theme today. Offshore wind gets more and more traction currently, and now is a solid pillar of all the plans for future energy supply, both in the UK and in Europe. We just had a discussion about the plans of Boris Johnson in UK, which is pretty impressive, and the European Commission has great plans. And so I think with this in mind, we have a good motivation for discussing offshore wind challenges today in this conference. And with this short introduction, I hand over to Andrew to continue introducing you to the show today. Thank you.
Thank you, Andreas. Good morning to everyone. A great pleasure to be co-hosting the conference with Andreas. So Fraunhofer and Eurecatapult, as Andreas has said, enjoy very strong research coordination and cooperation. And I think you see that quite a lot throughout the European community, that we are actually all very, very focused, not just in doing applied research, but doing applied research towards a purpose of growing the offshore renewables, or indeed the wind sector overall, because there's a lot to be done. So despite the many years of operation and the many gigawatts of capacity installed, I think everybody recognises there are still better ways of doing things. We need to keep the costs on a downward trajectory. We need to make plant more reliable, more efficient. We need to now be looking at how do we make these things more sustainable, so that we've got a longer term future ahead of us, because as we all know, we've got a massive role to play in renewables, in meeting the new net zero targets towards climate change. I think it's also worth bearing in mind, it's not simply about doing things for climate change. It's in parallel with that, growing our economies likewise, whilst we make these tremendous changes to our infrastructure that we've enjoyed for many, many decades through traditional routes of getting power into our homes and businesses. So for me, it's about applied research and doing it very strongly with centres such as Fraunhofer and others around Europe to grow that capacity, but also to grow jobs. And so we need to be focusing on providing business solutions. I think that's key, and that's why I'm very keen that these kinds of conferences, despite COVID, do plough on and address you as industrial partners and clients about what we could all be doing in the future. I'm very excited about that. I think the opportunities for us and our sector are just almost limitless in terms of where we can go. So I'm really looking forward to hearing what's going on today. I'm really looking forward to hearing from Giles in a second. But I'm now just going to hand you back into the Fraunhofer, and Christian is going to be our host for the morning session. Christian, over to you. Thank you very much indeed.
Thank you, Andrew, and welcome everybody. Good morning. Welcome you to my home office, which is kind of in the suburbs of Hanover. So as I'm the host for the first session, for the first part of today, I might introduce myself a little bit. Basically, I'm a mechanical engineer. I'm with IWIS now for about 8 years. and I serve as a head of department reliability and validation. In that department, we do have kind of two major pillars. One is questions on large bearings, damage propagation, and testing up to real scale for 6.5 meters. 3 test rigs are there already, 3 more will be there within the next half year. The second pillar is data science topics in operation and maintenance, questions regarding the value we can get out of maintenance and operational data, not only 10 minutes data, but also resolutions of 1 Hertz or maybe 1 kilohertz. Before I was started at EVIS, I've been in the industry for about 5 years, dealing with a lot of R&D topics over there. But anyhow, today I have the pleasure to host the first part of the conference. I saw there have been about 110 attendees signed up to this conference, which is quite good. There's a good share of science and companies, people being signed in here, and the company people are in the majority. For someone doing applied research, that's very good to have to see the interest coming from the application side. Especially I welcome all our speakers for today. And as this is a virtual conference, we would like to stay kind of close to the program, because we expect that some people might just join for specific speeches. So we trying to stay next to the program, and maybe I will interrupt our speakers like after 20 minutes politely to stay to the time. Questions and answers for all our attendees, you can type them into our system. At the bottom there should be a button saying Q&A. Whenever you like during a presentation, type in your questions. We collect it over here, and I will read the questions at the end of each speech. There will be a Q&A session. And as in any good conference, I invite you to add also to your questions your name and your affiliation, just to stay transparent who's with us. So I think that's enough structure for today. I will lead over to our key speech, to our keynote for today. Well, of course, everyone knows wind is not a national privilege, it's international, and therefore national and natural and international resource. So happy to get a view from what's on in the European Union, what's the strategy on offshore wind energy. So welcome you, Giles Dickson. Thanks for being with us, sharing your thoughts. I may introduce you a little bit. So Giles, in his early days, he was with the UK government as a civil servant, dealing especially with European affairs. In 2008, he changed to the French company of Alstom, where he served as a vice president for global public affairs. And for 5 years now, he's the chief executive officer of Wind Europe, and he's also chairman of the International Independent Advisory Council to the European Network of Transmission System Operators for Electricity. So, Giles, the floor is yours. I'm keen on your perspective.
Thank you very much indeed. I hope you can hear me.
Yes, well.
Excellent. Good morning, everybody. And I'm delighted to be talking to you on this particular day when the European Commission is going to adopt its new EU offshore renewable energy strategy, and on this day when the UK government is going to formally adopt its new 10-point clean economy plan. A word about Wind Europe. We are the industry body for the whole value chain of wind energy in Europe. Our members include the turbine and component manufacturers, the wind farm developers, power utilities, and many others. Where is wind in Europe today? The blue bars are the gigawatts of wind capacity installed in each country. That's onshore and offshore wind combined. And the red bars are the share of wind in every country's electricity mix. These are the numbers at the end of 2019. Wind, already 26% of Germany's electricity and 22% of the UK's electricity. Most of this is onshore. To give you a feel for that, I'm now going to show you this map with only the offshore numbers. There we are. You can see Wind energy is 15% of Europe's electricity consumption in total. It's 3% that is offshore wind. Now, what about the economic impact of offshore wind? Offshore wind contributes 7.5 billion euros to EU GDP every year. Every new offshore wind turbine that we install generates 15 million euros of economic activity. Today, there are 77,000 people working in offshore wind in Europe. If national governments across Europe deliver on their plans for the expansion of offshore wind, that number will rise to 200,000 by 2030. The International Energy Agency has said that wind is going to be the #1 source of Europe's electricity from around 2026 or 7 onwards. And from 2040 onwards, offshore wind will be the #1 source of electricity, overtaking onshore wind. I stress these are the IEA numbers. They are not Wind Europe's numbers. Now, in terms of capacity installations, Europe is going to be building a lot of new offshore wind over the next 30 years. It will actually build even more onshore wind. Here are the capacity numbers today. The dark blue is onshore wind installed in Europe today. The light blue is offshore wind. That's where we'll be in 2030. And this is what the EU want by 2050. And we shouldn't lose sight of that. We talk about the huge expansion of offshore wind. And in relative terms, yes, it's times 20 or more. But in gigawatt terms, the expansion still to come in onshore wind is even greater. But let's focus on the expansion in offshore wind capacity. What are we going to see over the next 10 years across Europe? What you see here is the increase in cumulative offshore wind capacity. It's color-coded by country. You can see the green at the bottom is the UK. It remains #1. And the dark blue above that is Germany. Many other countries are going to come to the offshore wind party over the next 10 years, including France, Poland, Ireland, and many others. Now, let's go back and recall that it's 450 gigawatts of offshore wind capacity that Europe wants by 2050. Where exactly are we going to put that huge volume of offshore wind capacity? Now, we did a study in Wind Europe last year looking at different sea basins, looking at different countries and their waters, and we assessed where does it make sense to put this 450 gigawatts, given where there is demand for energy, given the natural geographical potential, given the grid connections today and the future planned connections, and given the different environmental restrictions that exist in countries on where you can build offshore wind. And the answers we came up with were this. Of course, a lot in the North Sea, but it's less than half. A lot in the Baltic. The North Atlantic becomes very important, but so does the Mediterranean. And in fact, the Black Sea, we're hoping, will have offshore wind as well. Now, the North Sea, although less than half of the total, will still be hugely important in terms of the density of offshore wind farms within the North Sea. Look at this map. The darker the red, the greater the density of offshore wind. And you can see that zone off the Netherlands, off Belgium in particular, but look also in the Baltic. Poland is going to be a major player in offshore wind. Now, 450 gigawatts across the whole of Europe by 2050, that's a lot. Can we deliver it? Well, let's have a look and see what needs to happen in order to deliver this huge expansion in offshore wind. There we are, today's number, where we're going to be in 2030 and where we need to be by 2050. If we stick with today's laws, policies, and ways of doing things like maritime spatial planning, that is as far as we will get. We'll miss the 2050 target big time. We'll also miss the 2030 milestone. So what needs to change? Well, first of all, to get to the 111 gigawatts by 2030, We need a new approach to maritime spatial planning, more multiple use of sea space between different actors, offshore wind, fishing, shipping, military, environmental interests. We need to align processes, align the auction schemes for offshore wind across different countries. And we need to start building our first cross-border projects. These are offshore wind farms that have grid connections to more than one country. That will get us to the 111 gigawatts by 2030. But you can see it won't get us to where we need to be by 2050. So more things need to happen beyond 2030. We really need to embrace happy coexistence between offshore wind and all the other societal and economic interests that have a stake in Europe's sea space. We need to expand our supply chain big time. Today, the factories are producing 3 gigawatts of offshore wind turbines across Europe. Before long, we're going to need to be producing 18 gigawatts. So we need more factories, and we need many more of these hybrid offshore wind farms that have grid connections to more than one country. So if we do all that, we can deliver the 450 gigawatts by 2050. We have the technology and it is affordable. Now let's look at the costs. Here you have the auction results for offshore wind over the last 6 years. Spectacular cost reduction, as you can see, driven mainly by developments in technology. The standard new offshore wind turbine is now 8, 9, 9.5 gigawatts. That's what we're installing today. The 12 megawatt turbine is already operating in the port of Rotterdam. It will be deployed in the Dogger Bank by Scottish and Southern and Equinor around 2024-25. And we expect that by 2030, the standard size of offshore wind turbines we are installing will be 15 megawatts, and that will drive costs down even more. Now, of course, everything we're building, nearly everything we're building today is bottom fixed offshore wind, but that is going to start to change, mainly because of the geography. We can only do bottom fixed offshore wind in the red areas. That's where the sea is less than 50 meters deep. Everywhere else, offshore wind will have to be floating offshore wind, and floating is now coming of age. Today in Europe, we have around 60 megawatts of floating projects. There's the Hywind Scotland project. There is the new Portuguese project. We have another 300 megawatts that's currently being built and will be operating within 2 years. And by the end of this decade, we will have 7 gigawatts of floating offshore wind in operation, concentrated in these countries, led by Norway and France, but the UK playing an important role there as well. Equinor say we can get the costs of floating offshore wind down to the number you see here at the top of the 2030 chart, and we agree with them. The costs of floating will fall. They'll be driven by the growth in capacity. The quicker we can install 10 gigawatts and then 10 gigawatts and then 20 gigawatts of floating, the faster the costs will fall. Now, let me say a few words about these hybrid offshore wind farms that I mentioned earlier that will have connections to more than one country. Today, all of the offshore wind that we are building has point-to-point grid connections. One offshore wind farm, one cable back to the mother country, all very simple. But that is about to change. We're going to have different models. We're going to have something like this. The UK and the Netherlands are already considering this. They want to build a cable between the IJmuiden offshore wind farm in Dutch waters and the Norfolk wind farm that Vattenfall are developing in UK waters. Another model might be this. You might have an offshore wind farm in Norwegian waters, which isn't connected back to Norway, but is connecting into a central hub, maybe the Dogger Bank, which will have a lot of wind farms, of course, and then feeding back to the mother country. Or you might have offshore wind farms plugging in to an electricity interconnector between countries. You might have a big platform or artificial island built, which has lots of offshore wind farms connecting into it with AC cables and then DC cables going to 2 or more different countries. You might even have an offshore wind farm in one country which serves only one other country. All of these are models we will be developing in the future. And they make sense because they will enable us to pool generation and transmission assets. That will save money. It will also save sea space, and it will improve energy flows between different countries in Europe. There is, in fact, one such hybrid offshore wind farm that is already being developed, and it's in the Baltic Sea. It is Kriegers Flak. It has a grid connection already to Germany and to Denmark. We hope in due course it will have one to Sweden. Here is a very short video about the Kriegers Flak project, which I won't show you now. Perhaps we can later on if we have a little bit of time. But just remember how that looks. There are going to be many more projects like this. Now, there is Kriegers Flak. There it has the connection to Sweden. Here we have the IJmuiden Norfolk hybrid project that I mentioned earlier. What else is coming? Well, here we have the Danish, Dutch, and German governments developing a cluster in the North Sea. We have Estonia and Latvia who've signed an MOU to develop a joint offshore wind farm with connections back to both countries. Denmark and Poland want to build a hybrid project around the natural island of Bornholm in the Baltic Sea. And they're talking of putting the substations on Bornholm. They're talking also of putting electrolyzers on Bornholm so that you would convert the offshore wind power into renewable hydrogen. And then you would be transporting both electrons via cables to Denmark and Poland and also renewable hydrogen via gas pipelines. And then here we have the Dogger Bank, which I guess is the jewel in the crown of potential hybrid offshore wind farms, given the huge potential for the Dogger Bank and offshore wind and its geographical location right in the middle of the North Sea. Now, I talked about electricity interconnectors and the role they might play in these hybrid offshore wind farms. This is the map of electricity connectors around the North Sea existing and those under development. And some offshore wind farms might indeed be connecting into these interconnectors in due course. Now, I'm going to show you a map developed by TenneT, the Dutch-German TSO, now, of what they think the North Sea might look like in the future. TenneT want to build artificial islands in the North Sea. These are the hubs that you can see here. And again, just like on Bornholm, these artificial islands would have electricity substations. They would also have electrolyzers. And the blue lines you see here are TenneT's vision of the electricity connections back to the different mainlands. And the yellow lines are gas pipelines. And the vision here is to convert some of the North Sea's huge network of gas pipelines from carrying natural gas into carrying renewable hydrogen. Now, let's just talk about renewable hydrogen. Today, it is expensive. Here are the costs today. It is 4 times more expensive than producing conventional gray hydrogen via steam methane reforming from fossil sources. But those costs will come down, as you can see, by 2030, from the range of 4 to 8 euros per kilogram of hydrogen down to just over 2 euros per kilogram of hydrogen by 2030. And what's driving those cost reductions is the scale up of electrolyzers. The machines are still quite small, but we're going to have 100 megawatt electrolyzers before too long. We will have scale manufacturing of electrolyzers. And of course, the cost reduction in offshore wind will help to drive down the costs of renewable hydrogen derived from offshore wind as well. Let me show you an example now of one specific renewable hydrogen project. It's in Germany. It's actually an onshore wind hydrogen project rather than offshore wind. But what we're going to do here, and this will be operational by 2023, is take wind energy from onshore wind farms in Lower Saxony near Lingen in Germany, electrolyze into renewable hydrogen, put the hydrogen in a converted gas pipeline. It's 130 kilometers long. It will be converted to carry 100% hydrogen, and it will take the hydrogen down to the Evonik chemicals works in the Ruhr and the BP refinery there as well. And on the right, you can see the network that the Germans now envisage for an exclusive renewable hydrogen pipeline infrastructure. Now, we're talking about infrastructure. One key part of offshore wind infrastructure is this. Ports need to invest hugely in order to accommodate offshore wind. Every offshore wind farm, its equipment goes through a port somewhere in Europe. Ports need to invest in space. Look at the blades lying down here. Imagine that 12 megawatt turbine I mentioned earlier. Its blades are 107 meters long. Think how much space the ports need to have to accommodate all of this equipment before they load it on to the vessels. Then the loading itself. You need heavy loading quaysides that can bear 30 tons per square meter. Most ports don't have that today. That's huge investments in steel reinforcement of quaysides. You need deep berths for these jack-up vessels that come in and have all the equipment loaded onto them, as you can see here. Ports in Europe need to invest over 6 billion euros between now and 2030 to accommodate the huge increase in offshore wind volumes. A number of ports around Europe are actually members of Wind Europe. They're working closely with us. What do we need to invest in? What does the industry require from us? Please tell us. And they're sharing best practice among themselves and with the industry on all of that. Now, I began by talking about the economic benefits of offshore wind. Let me close by saying a little bit more about that. What you see here in the first bar is the 192 gigawatts of wind capacity offshore and onshore combined that we have in Europe today. Governments want to more than double that by 2030. This is the second bar. Fantastic. Look at the blue. What does that mean for jobs? It means that total jobs in wind rise from 300,000 today to 450,000 by 2030. That's onshore and offshore combined. But that means governments have to deliver on their volume commitments in their national energy plans. To deliver those commitments, they've got to change a lot of their policies. They've got to simplify permitting rules and procedures. They've got to have the right auction models in place for when they build new wind farms. If they don't get those things right, they won't hit their targets of 397 gigawatts. They'll end up in this third bar with 324 gigawatts. And you can see that that will have a really bad impact on jobs, because we won't be producing many more wind turbines each year than we are today. So we won't be investing in the supply chain. So the total jobs in wind energy will fall if governments don't get this right. Now, what specifically do governments need to get right? As I say, simplify their permitting rules, clear auction schedules, the right design for their auctions. And the UK's model for contracts for difference is clearly the best design here. We did not like that Nullgebot component that the German government were proposing for offshore wind. Fortunately, it's now been put on hold. We hope in due course they will copy the UK's CFD model. And of course, we need to keep investing in infrastructure, including the grid infrastructure as well as ports. Final word on maritime spatial planning. What you see here is Belgium's territorial waters, the Belgian EEZ. The red diagonal lines is where Belgium is building offshore wind. You can see it takes up a big chunk of their waters. The red boxes are environmentally protected areas. Then you have the fishing lanes, you have the shipping areas, you have the military areas. It's very crowded. We have to get maritime spatial planning absolutely right. Back again to the economic benefits of wind energy. Here are all the factories in the wind energy supply chain across Europe, making components for onshore and offshore wind turbines. And here, I suppose, is one of the jewels in the crown, the new Siemens Gamesa factory in Hull on the east coast of England. It's created 3,000 jobs in what was previously a struggling city. And here is an image of Bremerhaven, very familiar to many of you, not doing quite as well as it was a few years ago, but we hope that with the new announcements from the German government, we will see a regeneration of jobs and growth in Bremerhaven and the surrounding area. Thank you for your attention.
So, thank you. Great. That's impressive. I will jump on the video too. So, thank you for the presentation, Giles. That's an interesting overview to see what's happening or planned at our neighbors, not only our national plans to growing capacity, also see the neighbors. I may again give the possibility to our attendees to enter some questions. So there's the button at the bottom of your screen where you can write down questions in the Q&A. So I do have a question in for the beginning. You talked about those hybrid international or binational parks. Leaving the technical part aside, do you think there is any obstacles from the regulatories, for example, that make it more difficult or more time-consuming for offshore park developers to start the project?
Yes, there are. First of all, these hybrid offshore wind farms bring so many benefits in terms of saving money, saving space, improving energy flows across Europe, that we should have as many of them as possible. And the wind industry want them to be around 1/3 of the total offshore wind capacity by 2050. Okay, but to get there, you need to ensure that the wind farm developers have a clear economic incentive to invest in these hybrid offshore wind farms. Today, they do not. And they do not because it's not clear where their revenues are going to come from and how much electricity they're going to be able to sell from these hybrid offshore wind farms. And the reason for that is that EU law will regard these hybrid offshore wind farms as electricity interconnectors. And EU law says that wherever there is an electricity interconnector, the TSOs at either end of that interconnector must ensure that there is always 70% capacity availability in that interconnector. So if you are Ørsted or Vattenfall and you're thinking of investing in one of these hybrid offshore wind farms, you look at EU law and you say to yourself, oh, my electrons that I want to be producing might get squeezed out because the cables from my wind farm to either country are going to be treated as an interconnector. And the TSOs might dictate that the electrons that need to flow between the two countries take priority. Yeah, and they have a claim on 70% there. So I may not be able to sell very much of what I'm generating. So there needs to be a solution found to this problem. And the EU's offshore renewable energy strategy that's being adopted by the Commission today will map out some possible solutions to this. We think it's going to involve treating offshore wind farms as standalone offshore bidding zones in terms of electricity market functioning, with some redistribution of the congestion revenues that the TSOs currently earn, redistributing them towards the developers of the hybrid offshore wind farms.
Okay, thank you. So a question we got from Savinkova. Hello, thank you very much for the presentation. Do you think there will be a problem with curtailment growth due to oversupply of the wind?
Look, we need to invest hugely in grids, not just the offshore grid connections. Clearly, all these new wind farms have to be connected to the grid, back to the mainland, but we need to be reinforcing the onshore grid connections as well, okay? And we need to complete north-south link in Germany, north-south links in Poland and elsewhere. If we don't do that, then the risk of curtailment is high, yes.
Okay, next question from Paul. Do you see COVID as a short-term disruption or a long-term threat to EU's growth for offshore wind?
Yeah, the wind industry has actually proved to be very resilient this year. So all the existing wind farms, onshore and offshore, have continued to operate normally. Okay, they were regarded as essential services. We have always been able to transport the workers and the equipment to them, including across national borders. That's been fine. And in fact, the share of wind in Europe's electricity mix has risen from the 15% where it was at the end of 2019 to 17% at the end of June this year. Of course, electricity demand has fallen. Next point, the new wind farms, both onshore and offshore, the construction of them has continued pretty much normally, with some interruptions in some countries, but we've continued to be able to build new wind farms. And in fact, in the first 6 months of this year, we installed and connected to the grid over 5 gigawatts of new wind farms, including over 1 gigawatt of new offshore wind farms. We have also, despite COVID, in the first 6 months of this year, announced investments of 14 billion euros worth of new wind energy capacity, most of which is in fact offshore. 11 billion euros worth of new offshore wind farm investments announced despite COVID in the first 6 months of this year. So yes, we are confident that we can see through this.
Okay. A question from Andrew. What would you ask the industry and the research to do to help to deliver your vision?
Yes, keep working on those larger turbines, please. Keep working on balance of plant. Keep working also on the grid connections and on the HVDC technology. There's one very specific issue on HVDC, which is the 3 manufacturers of HVDC platforms today. That is Siemens Energy, Hitachi ABB, and GE. Their respective platforms are not interoperable. Now that's okay when your offshore wind farms only use one of the 3 suppliers because they only have one single point-to-point grid connection. But with the hybrid offshore wind farms, it's very likely that we're going to need to have 2 or 3 of the suppliers, their equipment working in tandem, in the same cluster. And therefore their equipment, their technology will have to be interoperable. And the European Commission is helping us with that, setting money aside within Horizon Europe for it, for a large demonstration project. So that is very good. Other things we need to be working on, recyclability of materials. This is a major issue already for onshore wind. It will become a big issue in onshore wind. We want the blades that we're installing today to be 100% recyclable. And that means, continued research, please, on the composites that we're putting in the blades.
Okay. Next question comes from Pedro Santos of the DTU. What are the trade-offs of seeing oil and gas industry take the lead on floating offshore wind and green hydrogen?
Yeah, look, the oil and gas industry bring a lot to offshore wind. They bring maritime experience, okay? They know how to work at sea. They know how to do health and safety. They're teaching us a lot on that. They know how to work with floating structures, extremely useful, okay? They bring know-how, they bring workers. Of course, offshore oil and gas in the North Sea is in relative decline, and offshore wind is in some way benefiting from the growing availability of workers who used to be in offshore oil and gas who can now come across and work for us, and they bring their skills and know-how with them. Of course, the oil and gas companies have very large balance sheets, and they can invest a lot of equity into projects, and that helps. Offshore wind today is around 70% debt financed, 30% equity finance, okay? And the more equity you can put into a project, the better, okay? The other thing that the oil and gas industry are bringing is extensive knowledge on how to work with local coastal communities and really engage coastal communities on the economic and social benefits of offshore energy, yeah? Now I know offshore wind on its own has been creating jobs in places like Cuxhaven, Hull, Bremerhaven, Blythe, Grimsby, and elsewhere. But the offshore wind industry really know how to engage with different community groups, including with fishing communities, and that's very useful.
Okay, so another question from Des Virtual. Very good speech of the event. If government can simplify permits, tech improvements, supply chain scaling up, and the other points you have brought up, what level of investment do you see as being a minimum level to reach the 450 gigawatt target?
Yeah, we don't like to put billions of euros numbers on this because we don't know exactly how the costs are going to evolve, okay? Look, we've announced investments of 11 billion euros just in the first 6 months of this year. Those are the sort of levels that we need to keep up, and we probably need to be investing even more. And don't forget, it's not just about the billions of euros you invest in the offshore wind farms. You need to invest very large amounts in the grids as well, and also in the ports. As I said, it's 6.5 billion euros that we need to invest in ports over the next 10 years alone.
Okay, so one of maybe last questions from Florian Vince. I hope I got that name right. What are the main bottlenecks that could act as a barrier for reaching such a growth for offshore wind in 2030 and 2050?
Yeah, slow and inefficient permitting rules and procedures, lack of headcount in permitting authorities. Okay, we have had some challenges, I'll be very honest with you, with the BSH, or the BSH, on this in recent years. The government recognizes that and has a clear plan to improve things, but we need improvements there in how the BSH functions as the main German permitting authority. The Dutch are doing this via their BWO much more efficiently than you are in Germany at the moment. Other bottlenecks, maritime spatial planning. Yeah, we need to start managing this differently. We need to be very sensitive and very careful about how we bring environmental interests along with us. Wind Europe has actually signed an MOU this week to create a new coalition with a number of environmental and biodiversity NGOs, including WWF, BirdLife International, and NABU. And we're very pleased with this because this coalition says we all agree we've got to expand offshore wind. We know that there's an environmentally friendly way of doing this, and we're going to work practically together to ensure that we do this in an environmentally friendly way. And this is good for governments because they know that the wind industry is taking its environmental responsibilities seriously. Other potential bottlenecks could include the military. The Swedish Air Force has already blocked 2 very large planned offshore wind farms in Sweden. Sweden is a laggard, by the way, in the development of offshore wind. They only have 200 megawatts. They should have much more, given their potential and given the fact that all other countries in the Baltic are developing offshore wind. And it's the Air Force more than anything else that's holding it back there. The Royal Air Force and the Luftwaffe are far more constructive, but military authorities can raise objections as well.
Okay, great. So overall, thank you, Giles, for a very impressive speech, and to all the attendees for your questions. That's very good and gives us a little broader view besides all the scientific and technical views. We will follow up the next 2 blocks today. So applause is kind of difficult in digital conferences, but like the deaf people do in this case. So again, thank you, Giles, for your talk, and maybe we can stay in touch here.
Let us, yeah. Great. It's been a pleasure talking to you all, and good luck. Have a very good day. Thank you very much.
Thank you.
Take care. Bye-bye.
Okay, bye-bye.
Bye-bye.
So we can go over to the first block. Giles already talked about the hybrid wind parks, wind farms. That's also presenting kind of a challenge to the grids. And interestingly, the first block has a main topic for the electrical infrastructure. So that leads us to our first talk here. I can welcome Dr. Colin McIver. It's great to have you here as well. Thank you for being with us. When we start the technical block for electrical infrastructure with a look at the current state, reviewing the regulatory arrangements for offshore wind networks, wind park networks, So a little introduction to Colin McIver. He is a research associate at the University of Strathclyde, and he's program manager of the Offshore Electrical Infrastructure Research Hub. And that is a 5-year collaboration with Eurocatapult and the University of Manchester. His research interests include the resilience and operation of low inertia power systems and various issues relating to the future integrated offshore network development in Europe. So Callum, welcome to the program, and I hand over to you. I mean, we're interested in what you have to tell us. So stage is yours.
Thank you very much. Hello, everyone. Is my screen sharing correctly?
Yes, works fine.
Great. Yeah. So, as mentioned, yeah. So I'm going to present a review of regulatory arrangements for offshore networks, and with a view to how we might, deliver these offshore networks of the future that Giles so eloquently introduced us to there. Just to mention that this work was with Professor Keith Bell and Dr. Andrew Madariaga contributed to this as well. Just quick background, yeah, as mentioned, this was done under the auspices of the Offshore Electrical Infrastructure Research Hub, which is this collaboration between Strathclyde, Manchester and the ORE Catapult. So it was about a 6-month project taken over the back end of last year and early part of this year. And just to say on that, a little plug for the hub is that we do follow a hub and spoke model. We're very open to collaboration with industry and new industry and academic partners. So if anyone's interested in finding out more about that, then please do get in touch. And Paul McKeever, who's chairing the afternoon session, leads things up from the Eurocatapult side as well. So this project specifically, the aim was to identify regulatory issues that will affect the design, deployment and utilization of offshore networks in the UK. So we wanted to do this via comparison of high-level sort of regulatory models that have been deployed across Europe and see what everyone else has done essentially, with a view to how the UK can really achieve these really ambitious 2030 and 2050 offshore wind deployment targets. Giles has covered much of this already, so I was just going to introduce by saying, what are we talking about when we say an offshore network? So there's sort of 4 main configurations as I would see it. The things we're used to seeing very much so far are radial connections of wind farms directly to shore. In terms of connecting countries, just point-to-point interconnectors. But going beyond that, we're starting to see, and we will need to see more hub connections where you've got shared transmission links for offshore wind farms and these hybrid grid connections where you're got dual purpose offshore networks. These can be delivered with either AC technology or DC technology, depending on the requirements and the distances involved. And just to sort of mention, the holy grail that everyone is really hoping to work towards is, some meshed or multi-terminal offshore networks, taking in multiple countries, multiple offshore wind farms. In terms of the regulatory regimes that can be used to govern the developments of these offshore transmission assets, there's sort of 3 main approaches if you look at it at the high level. So the first would be a developer-led approach, where the offshore wind farm developer would take responsibility for development and operation of the offshore transmission assets, basically in charge of everything up to the point of connection with the onshore transmission network. The kind of opposite approach to that would be a TSO-led approach, where the onshore transmission system operator takes responsibility for development and operation of the offshore transmission assets out to the point of connection with the offshore wind farms. In that case, the transmission asset might be part of the TSO's regulated asset base. It's essentially an extension of the onshore system. I should have mentioned in the developer-led approach, the sort of remuneration for that would be, part of the offshore wind farm tender process. And a sort of third way or third-party approach would be where a separate entity takes responsibility for developing that offshore transmission asset section of the network, and that would again be governed by a separate tender process. And it should be noted that the build and operation phases of these things can be separated. So there is the possibility for hybrid approaches, which we'll come on to a bit more when we talk about the UK OFTO regime. So part of the project was to sort of identify some of the key features of these different approaches. So looking at the developer-led approach first, clearly allows for inherently involves the ability to coordinate the offshore wind farm development with the offshore transmission asset development. So this allows you to do sort of bespoke grid solutions although what we've typically seen is sort of an optimization around the radial approach so far. And this is because there's, well, inherently a sort of low incentive within this model to consider any sort of longer term system requirements or holistic overview of what we might want to deploy as a whole. And so it's tended to be less suited to hub or hybrid approaches so far. But there is this high incentive to minimize costs via the tender process. Conversely, the TSO-led approach does sort of inherently enable this holistic view, this approach to offshore network planning. You can look much further in advance and try and coordinate things much better. So you've got this potential for coordinating designs and reducing the total infrastructure versus a multitude of individual projects. And if you've got a single entity leading that, then they've got potential for things like standardization and taking advantage of economies of scale to drive down costs. But it does introduce things, an interface risk between the offshore transmission asset and the offshore wind farms, which can lead to sort of delays or stranded assets. And if you are going to more complex designs, then you've of course got an inherently increased delivery risk, perhaps. There's a sense that the regulated monopoly approach also has low cost pressures associated with it, so it doesn't perhaps deliver at the lowest possible cost for consumer. And then there's the third party approach, and the features of which are really very highly dependent on the nature of how that tender process would be set up. So it could be suitable for any approaches really, depending on how things are set up, and it would have the high incentive to minimize costs via the tender process. But again, you've then got additional interface risks where you would require cooperation, multi-party cooperation at either end of your offshore transmission asset. So now sort of just go through a few of the countries around the North Sea really and see what sort of regulatory regimes they've been using and what that's led to in terms of deployed infrastructure. So starting with the UK, I mentioned follows this competitively tendered OFTO regime, where the network operator, the owner and operator of the offshore transmission assets are a separate entity called the offshore transmission owner, or OFTO. There's two options for delivering this. The first is a generator build option. So the offshore wind farm developer has the option to build that offshore transmission asset, but it then must sell it on to the OFTO after completion. In reality, this is the only option that's been used to date. The preferred option of industry is to build this link themselves. Despite there being the option for an OFTO build option, where if the developer declines to build the transmission asset, then a new tender process would be initiated for a third-party bidder to come in and design and develop this. So far, we've only seen radial developments really being deployed in the UK to date. Clustering and hub connections are, they're possible within the OFTO framework, but in reality, they're probably subject to a single entity success with multiple clustered wind farms in a tender process, and none of that's guaranteed within the framework at present. Thinking towards sort of hybrid connections, you can think there's probably going to be some difficult legal and regulatory barriers there as well, because OFTOs and interconnectors are very much treated as separate legal entities at the minute with different remuneration regimes. If we then move to the Netherlands, like much of its neighbours, it follows the TSO monopoly approach, so really the opposite approach to what the UK has taken. So since 2015, TenneT have operated as the TSO at sea. Grid connection takes place at the offshore wind farm. TenneT fully responsible for building the grid at sea. And this has been motivated by coordinated, centrally planned rollout of their offshore wind farm development. And TenneT have tried to make use of standardization in their process around a 700 megawatt design to try and drive down costs and try to take opportunities to share assets and cluster where possible. So far, we've largely just seen radial developments with some level of coordination where it's been sort of possible. Hub connections should be possible within the existing regime, but they've not yet really been implemented. In terms of hybrid connections, this again should be fairly possible under existing sort of regulations, because TenneT own both the interconnectors and the grid at sea, so there's going to be fewer sort of legal barriers to merging those two types of assets. Belgium is a very similar position to the Netherlands. Elia in this case responsible as the TSO monopoly. And they're building their modular offshore grid concept, what they've termed it, when sort of dubbed this as a plug at sea offshore hub, where with a transmission link to shore. And in this case, the offshore wind farm developers are responsible for connecting into this offshore hub or this offshore plug. And again, this is motivated by coordinated offshore development and trying to minimize the total infrastructure cost of this rollout. Hub connections are currently being implemented, so therefore in Belgium, and hybrid connections should be possible again, although there's a 50% TSO ownership rule for interconnectors at present, which might present some issues in sort of multi-terminal offshore grid scenarios. Germany, similarly, TenneT for the North Sea and 50 Hertz for the Baltic Sea are responsible for the offshore transmission asset development. And we've heard that TenneT have been the first to make use of large-scale HVDC deployment in a hub design approach as well. So 9 operational HVDC platforms, with more under development. Again, this was motivated by coordinated offshore wind farm development, and also the long distances from shore dictating the technology choice there. There's sort of well-publicized difficulties with some of the German experience to date, with some of these sort of stranded assets and delays coming to the surface, a perception that these might have been delivered at a relatively high cost. But despite that, Germany has been the first in Europe to market with HVDC hub connections already implemented. And as we also heard about before, they're the first, along with Denmark, to deliver on a hybrid connection, which is the Kriegers Flak combined grid solution, which Giles talked about as well. 400 megawatt link between 2 existing German and Danish offshore wind farms, and this has really sort of been facilitated by the ability of it just being a simple TSO to TSO cooperation. So there's no third-party ownership barriers there, and they've allowed this to be delivered. And I actually think I read yesterday that they gained an exemption to that 70% rule that Giles was talking about as well, which seems like good news. Denmark, the final country I'll cover, they follow the TSO build model to date. So they're an interesting case because, like most of their neighbours, they followed this TSO build model, but are now switching towards the more UK-like developer build model. So pre-2019, Energinet were responsible for offshore transmission asset development out to and including the offshore wind farm stations. But for their latest tender round for the new large offshore wind farm in Denmark, they're moving to this developer build model, and motivated by a perception that increased competition will drive more cost-effective solutions and faster solutions. And I heard at Wind Europe Offshore last year that this came about by listening to the industry essentially, and by that I mean developers, I think, is the preferred option again. So in Denmark, they've only really delivered radial developments despite the TSO approach to date. So clustering and hub connections were sort of possible within the older framework, but little opportunity for that to date. Again, they are implementing this hybrid grid solution at Kriegers Flak, but perhaps with the new model moving towards the developer build, there might be greater barriers to replicating that in future. It is a short study that we were involved in, so we didn't have time to look at a cost comparison of regulatory regimes ourselves, but we were able to look at 2 different consultant-based reports from last year who were able to tackle that question. And so this is a quick overview of what they found. The first was a German report by DIW Econ, commissioned by Ørsted, so an offshore developer. It compared 11 German offshore transmission asset developments with the offshore transmission asset developments at 24 British offshore wind farms. And did a levelized cost of energy comparison, which came out with the German developments had come in at a much higher cost of delivery. Now there's some obvious reasons why there might be a gap there, including the distances involved, the technology that were used, but they went through a fairly robust process of correcting for these different factors. And what they came up with was that there was still this sort of cost differential, which they suggested was a cost to the German consumer of an additional cost of 6.7 billion euros out to 2030. And they attributed this in the report to a lack of competition in the regulatory arrangement, and of course these interface and integration issues at the offshore wind farm and OTA interface, which we talked about before. One sort of criticism, not sort of criticism, but with a critic's head on, one thing that I think about this report is that, is it really fair to make a comparison between long established nearshore HVAC projects and very new far shore HVDC projects which hadn't really been implemented before in Europe? And perhaps doesn't account for a natural learning curve, which could potentially drive down the cost of future replication of HVDC projects. But the analysis itself was fairly robust on this. Another report was by the Dutch company Navigant, and that was commissioned by TenneT and RTE, so two TSOs. And interestingly, it came to almost the opposite conclusion. So it compared 6 GB offshore projects with a number of projects in France, Denmark, Netherlands, and Belgium in terms of the offshore transmission asset development, looking at subsystem level component comparison, at capex cost of substations onshore and offshore, and cables onshore and offshore. And its conclusion was that the UK offshore projects were deemed to be more expensive with higher costs for export cables and onshore substations in particular. And it concluded that the TSO development model therefore can be delivered at lower cost than even the OFTO model, and that's before you consider any wider system benefits of the holistic approach. Again, I think there was potentially some limitations to this study with a relatively small sample of projects, especially for in GB. It noticeably excluded the German examples we just talked about, and perhaps it wasn't really comparing apples with apples. There's larger scale, 800 MVA substation Dutch projects versus the maximum size in GB that was studied was a 400 MVA one. So perhaps economies of scale were accounting for some of this difference, not just the regulatory models, but some interesting oppositional findings from 2 different reports that were out last year. So just to sort of summarize what we found in those past slides, the GB OFTO developer-led model can be deemed as being successful to date. Competitive tenders have been seen to drive down costs, as we've talked about. However, it's very much been tailored to a radial approach. And the TSO sort of led model has been shown in some quarters to be cost competitive, at least, and it definitely allows for more coordinated approaches to be delivered. And really, what we wanted to point out in our report with a UK focus was that coordination will be key, and Giles highlighted that again as well. For the UK to deliver its 2030 and 2050 targets. And the reasons for that we pointed to are, firstly, to reduce the total infrastructure and footprint and therefore cost. And, there was a number of past studies we were able to point to that have alluded to the sort of cost reductions that are available through coordinated approaches. You really want to minimize the number of onshore connection points because public opposition is a very big issue. And you also just want to avoid duplication of effort into the same region if you can. And you really want to also minimize the extent and cost of onshore system upgrades that will help deliver this massive upgrade in offshore capacity. We know that some of the onshore transmission corridors in the UK are already congested, and upgrades are going to be required. It's just a matter of how large and how big these are. And again, the public opposition comes into this as well. So we made some recommendations in our report for how we might try and unlock some of these barriers to coordination in offshore network development, get over some of these hurdles. So, the first, and again, it's just reiterating the point that you need ways to develop incentivizing anticipatory investment. That's to build these hybrid or coordinated approaches. So one option for that would be to revert to what we've seen in much of the rest of Europe, which is a TSO-led approach. If you don't want to go down that route, then you might want to start thinking about allowing zonal developments within sort of the existing OFTO modeling framework. Sorry, not model. And if that means perhaps single entity ownership for some of that as well might reduce some of the barriers to developing it. Just give someone the authority to go and build out this coordinated development zone. We also sort of wanted to, highlighted the need to ensure that offshore wind farm project pipeline for the future, because without the pipeline, you're not going to build the networks. We highlighted the need to investigate ways of coordinating this onshore and offshore network development to minimize the total infrastructure cost. We suggested that, where possible, we want to retain a competitive tendering process because that has been successful in driving the cost down. And we suggested, there's probably going to be some legal regulatory reforms needed to facilitate these hybrid cross-border transmission projects as well. Now, that was sort of where we got to in our report, but I've just got a last 2 or 3 slides to say what's really happened in the last sort of over the course of the last year in the UK, and since we completed our own review and tried to feed some of this into some of the key stakeholders. But you know, that this topic of coordinated offshore networks has really gained traction in the UK in the past year, and it began in the early part of the year when Ofgem included in their decarbonisation action plan a reference to offshore coordination as one of their key targets for unlocking decarbonisation. And out of this spawned what's called an offshore coordination project, which has been led up by National Grid ESO, the transmission system operator in the UK. So they reported their phase 1 findings at the end of September for consultation. And I've put the link in here for anyone who's interested in that. But I'll just sort of summarize where they got to in the first few months of this year looking at this topic. So there was 3 main focus areas that they've looked at to date. The first 2 of which really affirmed the points that I've just made and we made in our report about, you know, the benefits of moving towards an integrated or coordinated approach. So the first report was a holistic approach to offshore transmission planning, where they did a technical comparison of following a sort of business as usual current approach with an integrated approach out to both 2030 and 2050. They concluded that, you know, most of the enabling technology is in place for the integrated solution, you know, but increased cable capacity and a commercially available DC circuit breaker would be helpful if they were realized to deliver their vision for 2050. They suggested that, you know, there would need to be some grid code and SQSS changes to enable this integrated offshore development that they've sort of putatively shown. But you know, they put some numbers around some of the things I was pointing out before there. So they said that, you know, up to 50% fewer onshore landing points could be needed for an integrated approach by 2050. And that might lead to a 35 to 60% reduction in onshore network flows by 2050 for an integrated approach versus the sort of business as usual radial approach where you're heavily relying on the onshore network to do the transmission. And this fed through to a cost benefit analysis where there were over £6 billion of savings identified by moving to this coordinated approach. Mostly in the capex, but also up to £1 billion in operational savings out to 2050. And this is just my final slide now. So they did look at what could be done in the regulatory sphere to try and enable this coordinated offshore network, but it's very much work to be continued. It was a short 10-page element to their initial report where they really just suggested a few high-level ideas. You know, interestingly, doesn't seem like there's any consideration for a shift towards a TSO-led model like has been delivered in the rest of Europe. And the suggested changes that they have come up with are all really, you know, incremental changes to the existing connection agreement framework with, you know, what I would term as a hope to enable a developer-driven approach to coordination. So they want to enable groups of geographically close connection agreements to be considered in a single process and enable closer involvement of the developers with the ESO in those group connection studies. They would like to enable bundling of a connection agreement with the seabed lease to streamline this and aid that certainty of the offshore pipeline. And, you know, they mentioned the need to review the allocation of risks and liabilities to incentivize coordination while giving confidence to developers and investors that, you know, they're still going to have a route to market. So really the detailed work is pending for phase 2 of this project. And, you know, I for one be very interested to see where they get to you know, to really show how these changes to the, you know, the existing framework can be made to deliver the required level of coordination. So that was my presentation for now.
Okay, great. Thank you, Callum. So now my video works as well. So thank you again for your presentation. That's impressive to see all the little regulations we have in Europe. Everyone has its own. That's how it works. I have a first question from Arno on these different national solutions or regulations. Do you think it's possible to go for a supranational solution to harmonize all the different regulations? Is that a possible way, or is it something that takes like 100 years?
Yeah, I think that's probably the issue, you know. Yeah, well, yeah, I mean, it was interesting just to see that there was just no consideration from the UK side of looking towards really shaking up the regulatory model. It's more of what can we change within our existing framework to make this happen. And I think that speaks to, I think the National Grid ESO are speaking very much with the stakeholders when they're doing this. And I think there's probably just other people can speak for this more than me, but probably just an outright rejection of that from industry in terms of wanting to get spades in the ground. They can't be dealing with years worth of regulatory upheaval. So often the case is try and go with what you've got and make that work.
Yeah. And you showed with your different, you look at different states or nations, the Danish changed their regulation, so change is possible, so to say. What do you think, is it for let's say Ørsted or companies planning a wind farm, is it a regulatory issue or is it something the companies can discuss? Is it an economic question to get the grid connection, or is it only a regulatory thing?
I think it's probably an economic thing, or getting project to delivery, and that's what's driven, certainly in the UK, just the radial approach is what we know and what's quick, and developers want to do it themselves because that minimizes the risk of relying on other parties to deliver your connection to shore, your route to market. So I think that's what's driven this developer-led approach, and maybe why the developers would like to have sort of lobbied for that sort of change in Denmark as well, and why they think it's good, and it makes sense, and it's worked, I think, to date. But the point is, we're in a new world where we need to deliver 450 gigawatts, so it doesn't necessarily work anymore under that framework. And yeah, there's big questions to answer on how you can change that and deliver these hybrid networks. And I'm not sure I've got the answers, but I'd be very interested if there's anyone else who can offer them up.
Okay. Well, we heard in the talk before from Giles that Boris Johnson is pushing the offshore wind goals for the UK. I don't want to stress the Brexit topic, but do you think there's any, looking at all the regulation, does it have any impact on hybrid wind parks? What do you think? Potentially.
Well, the issue of interconnectors, it certainly has sort of legal and ramifications for cross-border interconnectors, and even under existing ones, and we've seen delays to straight point-to-point interconnectors. So it will feed through, and whatever. I mean, maybe in terms of hybrid, wind and interconnector solutions, that needs to be a new solution anyway. So we'll work to what the new situation is going to be, but certainly, it's putting a hold on existing interconnector projects. That's already a certainty. So, yeah, it's not ideal.
Okay, so we reached our time limit, so that's good to get there. So again, Callum, thank you for your talk, for your very good slides.
Thank you very much.
It's difficult, so like this maybe.
Thank you.
We can stay in touch for the future.
Okay.
Hope to see you soon. We will transfer to the next talk. The slide is already on. So we switch to the industry side. In this case, after we started with the regulations, looking for some trends. So looking for the kind of the future. What's the thought of Dr. Aris Gutaras? Thank you for being with us. It's good to have you here, and we're quite interested in what you think from your side. What's the trendways where the grid integration goes to? I may introduce you right here. So Aris Gutaras is an electrical engineer. He has experience in power electronics for grid applications. Since 2011, he's active in this field of work. And since 2015, he's working in the wind industry, especially. Currently, he's with Siemens Gamesa Renewables as a key expert for renewable power plants and grid markets at Hamburg, I think, if that's correct. So welcome again, and hand over to you.
Thanks, Christian. You can hear me, right?
Yes, works well.
Okay, perfect. Thanks for the short introduction. And I'll just share my screen, and we can get So started. So I'll share. Let's full screen.
Yes,
Suggest this
that
has
works.
to go. Good. So I'll just minimize that also here. Perfect. So yeah, thanks, Christian, for inviting me in this block 1 of this virtual wind workshop on electrical infrastructure. I will be talking in the next 20 to 25 minutes about the trends in grid integration of not only offshore but also onshore wind. Show some interesting aspects from more from a control perspective of the electrical infrastructure. So it's a slide. It's a short slide deck, just 11 slides. Short introduction, then going into grid forming control. I'll explain what's that about and why is that relevant. And then talking a little bit about hybridization, a small part of this presentation, where hybridization, because both speakers before me used the term hybrids. In this context, we'll be talking about integrating storage units in the wind power plants. That's what hybridization means, and a few points about sector coupling, and then concluding the presentation with a short outlook slide in the end. A short introduction, grid integration of offshore and onshore wind. Some would say there are massive differences, different topologies, different challenges, but for the sake of this presentation, I'll just present them as two sides of the same coin. There are similar project factors that are decisive for both offshore and onshore wind. These project factors, these drivers, these are the drivers for the evolution of the electrical infrastructure of a wind power plant up to now. So I've tried in this table to list the different project factors and the drivers for the electrical infrastructure. I hope the symbols are clear. So that's offshore and that's onshore. So there are different factors with moderate or high relevance. For example, the number one factor for onshore, the LCOE, the levelized cost of energy, and the CAPEX, capital expenses raise, that has been ongoing and has massively influenced onshore wind business in the past 6 to 7 years. For the electrical infrastructure part also as well, at the first point, I've listed as reliability and OPEX optimization as of high relevant for the electrical infrastructure of an offshore power plant, because there are different. There's a different project size, there's a different risk, and also there are some additional problems related to servicing and maintenance of an offshore wind park. That's why the electrical infrastructure should be as reliably as possible and optimize OPEX and getting rid of unnecessary service work or repairing of components, and or changing component, exchanging components. And then the last factor would be dealing with increasing project and wind turbine size. So in the offshore business, the newest wind turbine, the biggest wind turbine, goes up to 14-15 megawatt. The 222 Siemens Gamesa wind turbine model, which is let's say a big step from the state of the art today. So the electrical infrastructure has to cope with this increasing project and wind turbine size, has to have some modularity to cope with these changes. In the onshore business, of course, there are also newest wind turbines, bigger diameters, but not such a disruptive increase on the size of the wind turbine. At least so far, we go up to 6 point something megawatt. Maybe in the future we can go also up to 10, but for the time being, the offshore is leading this area. So these are the four main factors that I have identified for this as an introduction. It's fair to say that also for the electrical infrastructure, also for the offshore business, the LCOE race will intensify in the next years. Also in the keynote speech from Giles, it was shown that the LCOE level has already dropped and will further drop in the next years because of the growth of the market, growth of the in different countries, or also with different investors and different operators. So this LCOE rate has just been warming up in the past years and will also intensify in the next decade. So the focus of the presentation is not really these 4 aspects of grid integration. It's actually grid forming control and also hybridization and sector coupling, and showing how these 2 aspects are linked with the factors on the left, with all the costs, the LCOE raise, and the increasing projects and wind turbine size. So moving on to the next slide, a little bit about the fundamentals of grid forming control, trying to give you an idea why is that even relevant to this discussion, to the electrical infrastructure of offshore and onshore wind. Yeah, exactly. Maybe these questions also are in the heads of the audience now. Why is it even control relevant to the electrical infrastructure of a wind power plant? Why we're not hearing anything about hardware, condition monitoring, predictive maintenance, or for the power electronics experts, silicon carbide, gallium nitride, new semiconductors up to 10 kV, or complex converter topologies or collector networks. These are all interesting points and also really important points. But for this presentation, we'll just focus on grid forming control. And maybe some will also think maybe grid forming control is just another control structure, control method that engineers came up with to keep them busy, to keep them occupied. So the goal of this presentation is just also to indirectly answer these questions. Why is that relevant to our discussion? Why is grid forming control relevant to our discussion? Yeah, so I've tried to put a one-liner for the definition of a grid forming inverter or grid forming control. It's extremely simplified. If you have any grid forming or power electronics control experts in the audience, feel free to use the chat and have another definition. But that's just if I wanted to use a one-liner for the definition. It would be the following. So a grid forming inverter is a grid inverter operating as a voltage source with a low impedance, actively controlling the output voltage and frequency. So why are we interested in this grid forming inverter? What can it offer for the grid integration of offshore and onshore wind? First of all, grid forming control grid inverter can be an enabler for weak grids and grids with high converter penetration. So also the speakers before have shown that the wind energy is growing, more and more wind turbines and in general converter-based generation is connecting to the grid. So grid following converters, let's say the state of the art of the control mechanism of the grid inverter of a wind turbine, have specific problems with high impedance grids and weak grids, and also need in some cases additional equipment to cope with grid challenges. So grid forming control would be an enabler for this type of grids. That would be the first point. The second point will be specifically for offshore grid integration. A grid forming control will be an enabler for cost-effective HVDC grid integration, and also an enabler for cost-effective island mode. And the third point would be really also an important point. Grid forming control would be an enabler for providing ancillary services. So far, if someone could summarize the role of the wind power plants in modern power systems in grids in a couple of sentences, someone would say that we are feeding mostly the available energy, and we are also reacting to transients in voltage and frequency disturbances in a grid supporting mode. But if we want to reach 100% inverter-based power systems, and not only 100%, but going further to 80%, 90% of inverter-based power systems, these wind power plants, these converter-based power plants should also take over additional services, grid services, or so-called ancillary services. So in the next slides, there will be these 3 bolded points will be discussed a little bit in more detail to give you a better idea of why are they relevant to our to our topic. And also establishing the link with the first slide with the introduction. All these points are related to project costs and economics of wind power plants. Another point also quite interesting or needs to be mentioned at this point, that grid forming control could be a relatively new topic for wind. Maybe there are people in the audience that hear that for the first time, but it's actually existing for a couple of decades in the power electronics control world, mostly for UPS in low power applications, industrial or residential applications, but also in the past 5 years, 5 to 7 years, in the portfolio of battery energy storage system providers for serving islanded off-grid projects that have also some renewables, wind, PV, etc., that go up to 10 megawatt. That's their, let's say, their scale up to 10 megawatt. So just a short parenthesis that this is not a new topic for the at least the converter world. Moving on to the first bold point, the first bolded point, grid forming control is an enabler for weak grids and grids with high converter penetration. The characteristics, if I could sum them in a couple of bullet points. So it operates as a voltage source. We have seen that also in the definition. So it has a stabilizing effect in any voltage transients, and also picks up load in case there is a transient with load shifting happening in the point of common coupling. Then the second characteristic would be inertia. So grid forming converters, if the energy also on the DC link is there, can provide instantaneous inertia and to reduce the rate of change of frequency when a frequency disturbance occurs, and in this way damping frequency transients. And the big benefit of the grid forming converter is that it doesn't need a PLL, a phase locked loop to synchronize to the grid. So it can react almost instantaneously. So within one grid period, within 20 milliseconds upon occurrence of the frequency disturbance. Another point that is not, well, it's not the focus of this presentation, but it's worth to be mentioned, power quality. This voltage source, this grid forming inverter can operate also as an harmonics and asymmetries sink. So just a couple of characteristics of grid forming control so that anyone can understand what we are, roughly what we're talking about here. So as I have mentioned in my previous slide, grid following control, the standard, the state-of-the-art control for wind turbines and also PV and also batteries, has operational limits with weak grids, with high impedance grids that have a low short circuit ratio. The phase lock loop is prone to instability, so the grid forming control can operate smoothly in significantly lower short circuit ratios. And also something that also needs to be mentioned, short circuit ratio is a standard term to characterize the strength of the power system, but it's not the only indicator for system strength. For the sake of simplicity for this presentation, we'll just stick to SCR. But in the future, there will be also other indicators of a grid stiffness and grid system strength. So for these locations where we have weak grids, where we have high impedance grids, we'll need a grid forming control to act as a project enabler. And these locations will be arising in the next decade. New projects will come in the area in the next years, both offshore and onshore, perhaps offshore a little bit sooner than onshore. So this is something that let's say the people that are interested or are relating to electrical infrastructure of a wind power plant should have in mind. And also another advantage of the single grid forming converters is that there is no need for additional hardware such as synchronous condensers. So one would say, okay, but even for these weak grids, even for these high impedance grids, we could install additional equipment, install additional synchronous condensers, which, by the way, in the past couple of years is also a new and emerging market because of these, mainly because of these problems of grid following converters. So if you have a grid forming control, at least let's say the stability part is taken care of, so there's no need for the installation of expensive synchronous condensers. So also taking the link once more, or establishing the link to the introduction, all these grid forming will act as a project enabler. So it's also cost relevant, or also is directly relevant to the economics of a potential project of a wind power plant. Good. The next slide would be about offshore, specifically about offshore grid integration. So the state of the art is for the HVAC standard array voltage up to 66 kV, and higher voltages will come in the next years. As the previous speaker has mentioned, also HVDC is an alternative state of the art for Germany due to longer distances to shore. The relevance of the grid forming control is first on the over voltage protection of the HVDC station. So by having a grid forming converter on the wind turbine side, you can have a better control of the voltage of the HVDC station, of the input voltage of the HVD station from the offshore side. And also another important point is that the grid forming control can operate as an enabler for alternative technologies, for cost-effective schemes such as the HVDC DRU, diode rectifier unit. It's not really new topology, the diode rectifier unit. It's just replacing the active front end of the HVD station with diodes. I have stolen this graph from presentation from 2016 from colleagues from Siemens Energy. So to reduce let's say the complexity of the HVDC station, and also the footprint, the size, the cost, one idea would be to install a diode rectifier unit on the input of on the offshore side of the HVDC station, but you need someone to control the voltage and also the active power flow in the offshore part of the grid. So that's why you need a grid forming control. Of course, in this case, starting up the wind park, synchronizing to the grid is not a straightforward task. You either need an extra AC cable or offshore some means of offshore storage in the wind turbines or in a centralized offshore point. So of course there are also some challenges included. Such cost-effective schemes, such alternative schemes are not yet established, mainly due to the risks coupled with a large-scale implementation. But as I have mentioned in the beginning, the LCOE race is intensifying. Alternative connection schemes that could reduce costs will emerge and will establish, so that the LCOE will also drop down to the numbers that also Giles have shown in his first in the keynote speech. Another point is the islanding mode. With grid forming control, you could realize an islanding mode. For offshore parks, that's mainly relevant because the grid connection can delay up to a couple of months. So having a grid forming wind turbine running on island mode can be useful to decrease also the size and the cost of auxiliary power supplies. And also grid forming control could be also an enabler for islanded offshore grids. And for offshore, let's say islanding mode is not that relevant, but there are also some use cases, for example, in typhoon conditions when there is no grid connection. and the wind turbine should perform some functions, some movements, then you need some type of islanded grid. So that could potentially also be relevant for the onshore case. Of course, islanding mode, just taking care of the consumption of the wind turbine with no huge load, has some technical challenges. So operating at very low generation level is challenging for the pitch structure of the pitch components of the wind turbine. It could also have a potential mechanical impact on the drivetrain. So this is something that needs to be investigated in detail. Once more, you'll see this bubble in each slide. These points are directly linked to project costs. To have some implications, or either capex and opex, or only capex, depending on the bullet point listed in this presentation. Good. One slide about ancillary services, which is relevant for both offshore and onshore. So by offering ancillary services to the power system, to the grid operators, the wind power plants will be able to have additional revenues through the provision of these services. Ancillary services could be, I could show a list of at least 20 services, but for the sake of time and because we have a broader audience, I'll just focus on these 4. So the frequency related and also black start. We have inertia, providing inertia to counteract on the rock-offs of the declining rock-offs because of increased penetration of renewables. Then frequency reserves because of mismatch of consumption with generation, providing excessive energy or reducing the energy. Ramp rate control. Sorry, one step back. Frequency reserves also have different names in different countries. Primary operating reserves, fast frequency response, secondary reserves. So I just bundled all of them in the frequency reserves point. And then ramp rate control or power smoothing, counteracting the variability of wind and the output of a wind, or the power output of a wind power plant. So that would be also an ancillary service. And the other is black start that doesn't really need a lot of explanation. These ancillary services are either relevant for grid forming or hybridization of wind power plants, or also both. I'll just give some extra points, some extra clarifications on inertia. So as I've mentioned briefly, grid forming inertia is counteracting the decommissioning of synchronous generators, and is actively competing with synchronous condensers. Some countries need that earlier than others. For example, in the UK, there's the Stability Pathfinder Phase 2 tender from 2020, considering also grid forming inertia, and Ireland will follow. Both of them are islanded grids that have seen increasing rock-offs up to a couple of hertz per second. So they need to search out to find out alternatives to counteract these increasing rock-offs. And black start is a really traditional. Black start is a traditional ancillary service in modern power system. Rules have not changed in the past decades. So, but in the next decade, because we have synchronous generator being decommissioned and we have hydropower plants everywhere, so the grid operators should come up with a more decentralized restoration plan that's based also on distribution level, to move away from the classical transmission-oriented central approaches. And grid forming wind can obtain a primary or a secondary role in such decentralized restoration plants, energizing transformers, energizing transmission lines, picking up parts of the load. But that needs a strict requirement is that let's say the restoration plan of the grid operators has to decentralize first. The UK is actively pursuing this, is actually working in this direction. The National Grid ESO and other countries will follow in the next decade. So of course, once more, the link to the previous slide, additional revenues, optimizing project economics, stacking of services to reduce costs for grid operators, not only for park operators, but also for grid operators. And that's, let's say, the last main slide, hybridization and sector coupling, that also it needs to be mentioned. So these both factors are, both points are key elements for driving forward wind penetration. This has also been mentioned in the keynote speech from Giles. The hybridization storage is counteracting wind variability, and we can have a more reliable provision of ancillary services. Not only when the wind is blowing, you can offer inertia or black start. So storage in combination with accurate wind forecasting will enable ancillary services from wind-based or hybrid power plants. And also we see a trend for a change in frequency reserves, in the procurement of frequency reserves, going from monthly contracts to having more agile, more flexible procurement mechanisms on a daily or hourly base, which is favorable condition for wind. Of course, there are different configurations for the storage integration, decentralized on the wind turbine or centralized on the substation. And the trend is going now from standalone battery projects in the UK and Germany to hybrid installations, exploring utilizations behind the meter. And as I've said before, stacking different services will consequently reduce costs for the ancillary services for grid operators. And just one point for sector coupling, there is the massive potential for coupling hydrogen production with wind. Of course, there are different integration configurations, and the offshore is a more appealing use case due to the higher capacity factor that also electrolyzers are more keen to. Yeah, once more, it's evident additional revenues leads to optimization of project economics. And as we have seen, the LCOE race, the LCOH race has just started, and the electrical infrastructure has to cope with the integration of electrolyzers in wind power plants. Last slide. The question is, the grid forming inverters are inevitable. The question is, how many do we need? That depends on the grid characteristics. A point to consider, I haven't mentioned that yet, so we have reduced short current. That's not something that the grid forming converters can do or can help with. We need some modified protection relay settings. We need new requirements for high voltage components challenging the status quo protection. And an essential step is to agree on the exact specifications of the behavior of grid forming inverters together with the operators. So my last point, we need a close collaboration between OEMs, park operators, and grid operators to find the best economic fit and agree on the specification of such a modified presentation. Christian, back to you.
Okay, thank you, Aris, for your interesting slides. Trying to turn my camera on as well. So now it works. Well, yes, again, thank you. The time slot is already kind of consumed up, so I think we have time left for one more question. Sorry to the audience, there has been some technical issues with the audio and at the end with the video of Aris. Aris, can you still hear us?
Yes, I'm still here.
Okay, so the video stopped. So sorry for the technical issues there. One question, or the first one I got, is on the keyword inter-vendor interoperability. Is Siemens Gamesa seeing some challenges by running wind farms on HVDC systems from different vendors being operated, in case of Germany, by different TSOs?
Well, I'm not the expert on this case, but to my knowledge, there are no problems in this area. So we are mainly agnostic on the connection of the grid integration and electrical infrastructure of the different vendors. So that would be my short answer.
Okay. Well, I will take a second question. Also, time's up. But how big of a positive effect on capex and opex could hybrid energy bring to grid forming control once electrolyzer technologies have scaled up and becoming competitive?
I mean, I cannot put a number on it. I can just say that it's a big potential. This is something that we are working on, and it's a relevant a relevant point for the future. So it's worth investigating. That's my also short answer for now.
Okay. And again, thank you for your presentation. We still see your screen, so I think we will move on to the next presentation.
Yes, should I take over then?
If you can, so I will spend some words on the transfer. So we had the first view from Siemens Gamesa on transfer grid integration, and the next talk will be the looking on test benches and the necessities of electrical tests from the view of Vestas, or especially of Christian Fenslau. Thank you for being with us. While the screen is still trying to change. Yes, now I can see you too. So Christian, again, welcome to the forum. I may introduce you. Many of you may know already Christian Fenslau. He's now with Vestas for quite a long time, since 2007. As a director, he was heading the Vestas test center with more than 50 different test rigs for various main components of wind energy turbines. Currently, he holds the position as a chief specialist test and validation. He's also heading the digital engineer lab as part of a strategic engineering development. And of course, he actively contributes to different research and standardization activities, not only in Germany, but also internationally. So again, Christian, good to see you on the camera. You can share your screen now, and we would like to listen to your perspective on testing electrical systems.
Yeah, thanks, Christian, for the introduction. It's a pleasure to be here. I hope everybody could hear me, and screen and sharing is in good condition.
Works well.
Perfect. Yeah, that's the first step always in this new way of presenting and working. Meanwhile, I must say, especially also in all these international committees, it worked fine, and everybody has accepted it. And most challenge is still the time zone to get nearly the entire world at the right spot. But I think in this case, it's much easier. We are still at European time. There's only 1 hour difference between UK and the rest of Europe. Yes, I will give you a little bit input about why Vestas is thinking about the way of testing as it is, or as it should be. It is a little bit less technical as the presentation from Aris. So it's more seen from the Vestas, from the business value and from the strategic point, how to get the things done. And of course, we are always looking for solutions. And yes, let's start. I need to check if one second. Now I have a challenge to. I have put on the wrong window. Yes, here it is. I think I do not need to explain who Vestas is. I hope that everybody knows what Vestas is. We are 25,000 employees. We have, meanwhile, more than 108 gigawatt under service of our turbines, more than 122 turbines installed, 12.1 billion euro as the revenue in 2019. And we just had 2 weeks ago, the Q3 result also for 2020. It seems not too bad, seen in the perspective of this Corona impact and so on. So this also indicates that the wind industry is still full speed running up. Also looking across the different countries, all these climate and CO2 discussions ongoing, and the indication seen from the orders we have in the books, and I think that's the same also for some of the other competitors, is still on a high level. Where's enough of the cake for everybody, I would say. So, and that's also important that we work together in some cases to move forward in changing the industry. As it's still a pretty young industry, but
the speed is not stopped. If we are just looking on our product portfolio, what we have meanwhile on, it's a wide range, looking on from still 2 megawatt platform, V90s introduced in 2004, up to the new Enventus platform, which is going up to 6 megawatt. And this even does not cover the offshore part, as you might have also heard in the news that the offshore part will be rejoined Vestas after all these governmental approvals are done. So might be by end of the year, might be in Q1 latest. But so far it's still separated and we need to keep it separate. But anyway, to see this one, it's a wide range that needs to be covered. I must say I started in the wind industry as a young student at an institute where at that time 1 megawatt was a really, really huge turbine. And then also the 2 megawatt came up soon, and then everybody thought, might be a little bit. And now we are talking already onshore on 6 megawatt, but even offshore, looking on Siemens and GE, we are in a range of 14, I think 14 plus, which Siemens has introduced. So, and that I believe it's not the end, so it will still continue going forward. This also brings a lot of challenges in design and also in the business. And just a little bit looking on the business, that is something that has definitely changed over the years. When I started, it was, let's say, are these nerds doing something for the green stuff and looking forward, and it was not really a business, I must say. Meanwhile, everybody is looking on the cost, and it's about the cost to produce the electricity on the end, so the levelized cost of energy, driven definitely by the turbine cost. And I found a good overview about where some clever guys have collected from the different sources the input. What is the turbine cost at that? I think this only covers the US market, but it could be also extended to other markets. So it's definitely the trend is going further down. We are now, I think, in a range compared from dollar and euro. I think it's around about a little bit more than 700 euros, 1,000 euros per megawatt. And of course, this is a challenge also in the design, as not only the bill of material is driving the cost, so sourcing of different components and so on, but also how to make the designs. The other part is, as I just showed, the amount of turbine variants available and just for Vestas. And if you put on also the ones from Siemens, GE, and Nordex, then it's a wide range. And compared to the 20, 30 years ago, then it might be was one turbine every second year. Looking on the market, I think there's nearly each quarter someone announced a new turbine variant. And then next month, the next one is following, just to have the next bigger or higher turbine available. So this time to market is also something that drives the activities in the design. So it's not that everything is ready and everybody could just take the blueprint and just make a little bit bigger. It doesn't work, then you would not meet the trend about lower cost. So this is, of course, challenge in the design, but also to verify design. What we are looking on, and I will jump a little bit away from these business drivers, look a little bit what the testing area at all, and it's specific in Vestas, is addressing in it to get these things catched. Just looking on why we are doing testing. And I'm pretty sure that it's similar for our competitors. I think it's also in different industries, it might be the same. So it's most likely looking on continuous operation to ensure that the product's always working 24/7. So that you could ensure, and especially our customers on the end, ensure that they have a business case certainty. So ensure that also in 1 year, in 2 years, in 5 years, the turbine is running 24/7 and produce electricity, which is for them equal to money. Of course, reliability is the next part. You could run a turbine 24/7, but if it breaks down after 5 years, then it doesn't help you. Then you need to have high service and repair costs. So also to have a reliable product that runs up to the end of a design lifetime. So most likely in the wind business, meanwhile, 25 years, some still 20 years. So in the range, and also looking on some of the old ones, whereas these extension to get them still operating for might be 30 years. And what everybody has also in focus is optimization, to get as much as possible out of the machinery. So to have, from the performance-wise, the best turbine, also to minimizing the cost. Each kilowatt hour you're producing more is, of course, improving your business case. So you're minimizing you're maximizing the outcome on the money you earn. So if you're looking on all these three topics, all are also very much close to some money. And on the end, if you're looking in the market of wind industry, there's meanwhile a lot of customers. They don't take care how they make the money. They just want to have something that produces green energy. It could be wind, it could be solar, it could be something else. So they just need to have these green touch in his companies. And you could look on the big Googles and IKEAs and who else. They all want to have it, and they all put it on as advertisers. But on the end, they just don't take care about if it's a wind turbine or solar panel or what else. So I think also seen in this, I would say the competition inside of the wind industry, this is not really a big thing. It's most likely the competition between the wind industry towards solar or some other industries. How could we as the entire industry work together and make our industry, our products better and competitive towards solar? Looking on the production cost of turbines compared to solar, you find meanwhile several areas, several countries where solar is far cheaper than wind turbines. Even turbines are meanwhile very cheap. If you're looking on Mexico or what else, where in these auctions, it's regular that solar beats the wind area. And that's where we have our challenges. And that brings me back to the testing. So if you're just looking on the electrical testing. So the grid compliance, I think you are very familiar with these. You are all from this area. The state-of-the-art part is that the classical grid compliance test is done with the FVRT containers on site. You connect it between the grid and the turbine, and you're running this according to several standards. You're running it according to the needs from the TSOs. And of course, you have a hell of local regulations. So I'm not sure how many different grid regulations are available across the world, but even in Europe, there's still a lot of different ones. Even there's a trend to get this harmonized, but still it's a long way forward. And Christian also mentioned in the introduction that I'm also part of some of these international committees, whereas liaisons between IEC, ICRE, and ENTSO and so on to get this done. Especially ENTSO is working on these things in Europe. But we are international suppliers, and that is for I would say everybody in the wind business. So we also need to cover Indian markets, Chinese markets, and so on. And this is, of course, a challenge if you need to have always some special tests done for them. Of course, the implementation itself has some challenges to get it done on a turbine. You need to have people involved, be on site. You need to have the accreditation institutes on site, so the ones who is allowed to make these tests and put the right stamps on, like the IEC RETLs. They're the only ones who are allowed to make this. And on the end, also the certifier and the network operators, so the TSOs. So it's a lot of activities around a turbine. In the implementation, we have also a lot of challenges. If you just think a turbine, it's a prototype, you first need to build it. It's most likely on the end of the developing phase. So when you have the design done, when you have started the manufacturing, and then starting to do these tests, in the execution, you need to cover these different requirements. You might need to repeat tests again and again with different parameters. you have a high uncertainty in the wind condition. So you're depending on the wind, when does it blow, when not, and that could easily increase the duration of a campaign for 1 year. Just having in mind how many turbines are expected to be bring to the market each year from everybody, then 1 year is a long period between one variant and the next one. So might be then meanwhile the next variant is already announced before you have finalized your tests. And of course, the demand on the test capabilities, just looking on the trend of the size of the turbine. If you're taking worst case, the offshore turbines, so taking containers for 15 megawatt, it's of course a completely different size and setup compared to the traditional one used on a 2 or 3 megawatt one. And thinking forward, is it really the way to do the things, putting more and more on? Just thinking a little bit more out, how is it done with other kind of power plants? If I see the turbine just as a power plant, just looking on a coal plant or nuclear plant. So we have much more power, but do they have FERT containers? No, of course not. Of course, they have also some different challenges. But this is also something that triggers the idea, how could this be done differently and more closer to something that is done in other industries? Yeah, and all in all, it's still in the end, again, the cost. It's always the cost. So just thinking about all the uncertainties in this and increase of time, having people somewhere and prototype locations, which is most likely not close to the design departments, having them travel it forth and back and so on. So the cost could be easily go up to 1 million euro or even more. So it depends a little bit on the setup. And I must say these numbers, it's not Vestas numbers, it's general numbers across the industry. So what we thought about, let's look a little bit in what we in Vestas have and how we are doing tests for some other ones and how could we address this. We just look on, okay, we have a huge insight in our turbines. We have more than 122 gigawatt installed turbines. So, and a huge number of these, we are monitoring like everybody is doing, getting permanently data and see how this works and so on. We have climate data, we know the industry benchmark. So we have a lot of information, how is the reality of the existing turbines. And then it's a question, how could we use this in getting these moved forward, how to change the test, the verification concept for the grid compliance. The next topic is the experience. Just looking on Vestas, we have more than, meanwhile, I think it's 20 plus, it's meanwhile, I think 20 years experience in different kinds of testing across a lot of turbine platforms. And of course, this is also something in how to make tests. So one part is to know about the product. The other part is to have the knowledge in executing tests. I think everybody could buy a test container or a test it or what else if they have enough money. But how to use them, how to create value with this. This is something that could be not just buy-in by having some clever people or some standards following. Of course, standards is always the basic, but the more advanced one, you have always your own protocols and based on your experience. And then the last topic is having the test methods and the test capabilities. So creating with the knowledge from the inside and from the experience in testing, creating unique test methods. If you are looking in the industry, as I mentioned, we are still a young industry. Of course, you have meanwhile more and more test methods predefined, but there are still a lot of things that could be done differently and more smart. And just looking also on the applications in the IPR, so the patents coming in, it's amazing how many patents are still raised in the testing area. So this is definitely also an area that is important. And on the end, if you would think differently going out from a test on a turbine, it's also the question about the hardware that you have. Do you have test capabilities, test switches that are capable to run this? And Vestas, I would say it's a little bit driver in these test capabilities. We have started this journey quite a while ago, spending a hell of money in test capabilities. We could see that meanwhile, also independent test houses like Fraunhofer or Catapult or Lord in Denmark have invested in this, and we are really happy to see this, as on the end it supports us and the entire industry. But also our competitors, I think, jumped on the train and have seen that this is beneficial. And I must say I'm a little bit proud about that this is so well accepted, and this is, let's say, the industry have followed what we have introduced 10, 15 years ago with these big test switches, and I think it really provides benefit. Yeah, and of course, fully integrated test, that is a little bit special for Vestas on this. Just a little bit about Vestas testing once more. It's not so much related to the grid compliance test, but to give an introduction about this, testing is going across in different areas. Of course, Denmark has a strong focus with prototypes and different test switches for generator, converter, and gearboxes, and so on. And Isle of Wight in UK about full-scale blade testing, pitch bearing, and so on. And even in Chennai, in India, we have test capacities. What is important, this is also that we have a lot of prototype turbines, most likely in Denmark, but also using customer turbines to get these done. But just imagine traveling around in Europe, and even now with the Corona time, this is definitely a challenge. Just to move from Germany to Denmark or even to Sweden is a challenge by itself. And then putting this in the perspective, creating it for a test setup and getting a test done in time, that does not make it easier and definitely not cheaper. So back to the testing, of course, testing methods, and that is not specific for Vestas. I think that is for everybody. There's different steps in testing. There's most likely things on proof of concepts. You have design tests, process tests, prototype, and product validation. What I mentioned is with the in the beginning also with the grid compliance, just looking on when typically a grid compliance test is done is most likely as one of the last steps. So it's on the prototype, that's when a lot of things done already, and there's not really time to change as the production has already started. And if you find something out that needs to be changed, it's far too late, or at least very, very costly, and has an impact in your timeline. So the thought is, how could we push this forward? How could we get it done in an early phase of the design, might be even as a part of the design? So then you have, of course, more flexibility. Then you could make changes with less cost impact. And of course, you need to provide the same results as on the end, as this one is certification relevant, and you need to have an acceptance by the certification by the end, on the end. Just to recap a little bit on the part where we start with the grid compliance. So the idea was, what is it that that could be done by using all these good things we have already? We have the experience, we have some test capabilities, we have inside of the turbines, how to get out from these setup of testing on the turbine with the containers. And therefore, we have started different initiatives and joined some of the initiatives. For example, the Hybrid Crop project together with Nordics, Fraunhofer, and at that time also Senvion, which meanwhile disappeared. And that is something, I think Torben is the next one who will explain how we have made this in a different setup. We have fully supported this. On the other hand, it was also important to get the standard, the specifications, the guidelines addressed. It doesn't make any sense if you have a great setup on a test switch, that works and provides the same results as long as it will be not accepted by any certification body. So that's why we also initiated together with Siemens a new working group under the ISC for the -21. Now we have a -21-4 that is specifically looking on the way how to get these grid, the electric characteristic certified by using test equipment instead of a full test on the turbine. And these are the parts where I think it's a very good example that the industry could work together, and it makes sense. Just looking on other industries, that's very common to do this. If you look on automotive, it's normal that they do things together. They are defined. Of course, some at the last years have a little bit overshooting, especially some of the German suppliers. But this, I think, is a different story. We are very well aware about that. We need to be careful, not running in any legal issues, but looking pure from the technical part, it makes sense, and we are driving. And I think it's also a little bit an advertiser for the next presentation to see how this is addressed with a completely different setup. And the intention was really to make you aware about that where is the business need for thinking differently to come to results. It's again, just to repeat, it's cost and time. So how to get this done in a smart way. We have a lot of possible solutions meanwhile, and also capabilities using new technologies and so on that makes it happen. That is also all so far from my side. Any questions? I must say I have not looked if someone has raised the hand in between or raised already a question.
Anyhow, first of all, thank you, Christian, for your presentation. Come up with a video. That's a nice overview you gave here. I think we have time for some questions left. So if anyone has a question, just put it into the Q&A chat service, whatever. I will start with a question. Christian, you talked about customers kind of changing, going more for being less interested, taking less care for how the turbine works. Well, we know from operators before that some are very interested in technical issues with the turbine, others just economically, and let's leave the technical stuff to others. Do you think that the ones you just mentioned, like Amazon and others, they are different than these whole approach of non-technical operators?
Yeah, we clearly see there's a change in this. We still have the ones who would like to have a deep technical dive, and of course, also someone who's just looking on the business. They're asking some consultants to help them to find out if this is something makes sense and how is the risk. On the end, also the one who's giving the money would like to know what is my risk left over in this. And we are asking consultants to make this evaluation, to go in, someone with experience, but on the end, the end users itself, they just have an interest to get these done. So I think there's a huge word for consultants who are very clever and could give the advice, supporting these companies. But of course, we are still also the companies who have an own interest. They are, let's say, more technology-driven companies to looking inside how it works.
Okay. I have a question from Paul. Your approach to testing at all design stages is an approach used like in automotive. Do you see this being incorporated into offshore wind anytime soon?
Yeah, I think especially offshore wind is important. As the risk in offshore is even higher as onshore. That is not a surprise, and I think we all have made our experience in the offshore part. It's not a secret. So testing, I think, is essential to ensure that you have these business case certainty, that you ensure that your turbine operates also in the harsh environment of offshore over the time. So just looking on the North Sea, we all know that it's not so often that you have the chance to reach to the turbine. If there's something going wrong, then it still needs to work.
Okay.
And testing is still, anyway, looking on all these simulation things coming up and looking on this. Anyway, you are doing more and more on these virtual parts. Still, any kind of model needs to be validated. So I think there was a clever guy who mentioned that all models are wrong, might be some are useful. And I think that's still valid. And you could make them more useful if you are making the right model validation. And that means bringing the reality, bringing information from operation fleet, from testing into your design and make this validation. And model validation is much more as just putting two numbers beside and say, yes, it fits. Honestly, I have seen too often this. And then if you just vary it a little bit, then, oh, my model is wrong again. And just might be for your information, there is a joint working forum between the IEC and the ISCRE that is just focused on this model validation. We had a little bit paused. We are just restarting in December, looking at how could this be formalized for the industry, how to make model validation. And it's not on, it should be a more generic approach, but of course we have started to looking on the power performance first as the easy one, I would say, and there's a high interest in the industry to get this done.
Yeah, I fully support that approach on testing and validation. Models always have errors, and it's too easy just to compare one code to the other and saying, my virtual model is kind of similar like the other virtual model from another software.
Yes.
So where's the gap to reality? So I would go for test and validation as well. Okay, so I will now lead over to the next presentation. Thank you again, Christian. So now after two presentations and perspectives from the industry, we come to the view of science and research again. It's still about testing and electrical properties and look to the future on the grid. So the next presentation comes from my colleague Torben Jersch. He's an electrical engineer, of course, and he's head of Department System Technologies at Fraunhofer IWIS. His unit focuses on developing test methodologies for the needs of the change of energy systems, and his own studies already were on grid integration testing and designing new original test benches for multi-megawatt wind turbines. So Torben, welcome to the program. Thank you for being here with us, and now I hand over to you.
Can you hear me?
Yes, yes you do.
Okay, perfect. So yeah, Christian, thanks for the introduction. Now I will also try to share my screen. It's always the same here. So.
Yes, now we can see your desktop.
Okay.
Full screen presentation. Okay.
Okay. So again, thanks for the introduction, and also to Christian to give me a small introduction. What I would like to introduce today, okay, what we're doing on this electrical testing of electrical properties of wind turbines on test stands, and how we do it and what we see, what will be the future of it, and because are cropping up some new requirements. But first I want to start with a first introduction, and then coming to the Hill Grid Core project, and then finally to the outlook. I hope that I will be in time because it's a complex topic. So yes, but I will start. But starting, so where are we coming from? I'm working now since 9.5 years at Fraunhofer IWIS, and more or less from the first day I've was working on this electrical testing on huge test benches since my third day at Fraunhofer IWIS. So this is more or less developed by a lot of ideas coming from our team. And we have started with this in 2011. But at the moment, we're running our Dynalab test facility for testing nacelles and doing this certification testing of electrical properties. We're running it with roughly 33 employees plus students. And this is not only doing the testing, we do all the engineering stuff around this, like the mechanical and cooling integration, but we are running and developing our grid emulator. We are handling all the automation systems, but of course we're a research institute and not only a company running a facility, so we're doing a huge number of research projects in parallel. So, and the Dynalab test bench was commissioned in 2015. And since there we have tested 7 different specimens of these companies. But also coming back to the idea, okay, where was this, or why it was cropping up? What Christian has explained, it is really expensive and to do the grid integration testing in the field, and this is done normally in the end of the development phase when the prototype is erected. And so I hope you can see my mouse much better now. So you're doing this really in the end during the field testing, and compared to an ideal design and validation process, normally you're doing a lot of testing here in the lower level of this V model, because when you find some failures and errors in your system or in system design somewhere here above, it will get more and more expensive, so the pain will get bigger. So if you find your errors later, so there's the idea to bring all the testing as much as possible down in this V model. And the approach was coming from field test going to the system testing, and our new approaches are here doing this on subsystem testing. So, and how it is looking in case of our activities at Fraunhofer IWIS. So this is doing some testing on a cell level. This is then our Dynalab test bench, and we call it minimal system, or you can call it also generator inverter system, doing all the grid integration testing, also in a test bench. Therefore, we have our HillGridCo project. And as Christian also has mentioned, the field tests, they are described in the, for example, in the IEC 21-1, and we're also working in the standardization committee, so this is -4, and there's the idea that we describe how to do tests on both of these levels, and that these can also be accepted for certification purpose. So, and therefore 3 years ago, we have started the HillGridCo project with Nordex Investors and also Zenvion, but due to bankruptcy, they are out, unfortunately. And what we are doing here, I will try to explain it to you. So what we have done, this is a sketch of our test bench. So we have here our prime mover. This is motoring. This motoring fast running generator and a converter system. Here, of course, I've sketched a Type 4 wind turbine model, but it's also possible with Type 3 wind turbine. Type 3 wind turbine, so with a DFG. And what we're doing, we are motoring here with a test bench. We are motoring the system, but what is special in this approach, what we are following, when not only running in a speed controlled mode, we are do an emulation of the wind and or the rotor and drivetrain dynamics, we emulate it by this high dynamic motor here. So at the moment, we have built it up, and so this is our actual setup. If you compare it to the dimensions of the Dynalab test bench, so this is really a small setup, not from the power, but from the mechanical dimensions. And this will lead definitely to huge reduction of the logistics and mechanical works, so that we can accelerate the testing, but we can also decrease the cost for all the adapters. So with this setup here, we hope that we can drastically reduce all the grid integration testing and test benches compared to the huge nacelle testings. And then it will also make sense to do only this grid integration testing inside the lab and not doing it in this huge nacelle test benches. And what we do then also on the grid side, we have here the emulation of the grid behavior, and in this project we are using here our, let's call it, old grid emulator. We're using this from the Dynalab facility, and by this extension we are now also able to run on the public grid here, or we can change the grid emulation. And also here, this is not only for providing some voltage checks, it's also for providing a realistic grid behavior. So how is it looking in CAD, so that you get a little bit better overview? We have here our motor. This is a 9 megawatt. This is a 9 megawatt drive, but with an over capability of 13 MVA. Behind this, there's our cooling yard, and behind this, there's the inverters. We have installed inverter capacity of 26 MVA, and this is due to the reason that we need a lot of more capacity for our dynamic control. For the cooling system here for the DOTs, we have two connections available. Normally it's used, one for the generator, one for the inverter, but we can control the cooling system separately from ours. So that's also the possibility to do some generator testing for some heat runs, for example. Here we have a special adapter designed. There's a lot of tons of steel. I think it's 12 tons of steel to create a very high eigenfrequency, so that we do not have any excitations from the generator will be adapted here, that there's no resonances. And what I've also mentioned in the beginning, the most also the biggest advantage and new thing, this is this hill testing, and I will come to this in the next slide. So this is looking now a little bit complex on the very first view. So, but we have here our DOT, what will be tested, and of course we will connect it here at the fast running shaft, and then we have here our driving system, and the set points for our drive. This is coming from our control and hill controller, and in parallel we are running here we call it MOVEit. This is our wind turbine simulation program, with also running on real-time machines. So this is then providing over Ethernet real-time interface some set points to our test rig main controller, and this provides the set points to the inverter unit. And of course, we have to couple here the field bus from the system, because we want to have a one-to-one controller interaction. So the wind turbine controller or the inverting controller must react on what is happening here in the virtual rotor, that it seems to be running in the field. Therefore, with this idea, then we can really operate in field-like conditions. And of course, this is also a complex. This is a complex setup, but all these interfaces can be standardized, and so that the efforts for integrating it a second or third time with a company can be reduced a lot. One small outlook. So what we're doing, we are able to run some very, very simplified virtual models, and then we normally run it on a back-off control. But what we have seen inside the project, due to, for example, individual pitch activities of the turbines, it's getting hard to use the simplified models and apply the correct behavior to the wind turbine controller. So now what we're doing, we are running, we are doing our load calculations with MOVAT. We're getting some wind turbine models, and then we do model reduction that we can run it on an Opal RT simulator, and then we run the wind turbine models. So the detailed wind turbine models is a 5 milliseconds. We are running it, and this will then again provide it to our drive unit. So, and one very important point from our side, this is one thing is, okay, in principle we can do it, but as Christian has also mentioned before, there are a huge number of markets. There are a lot of different tests. There are a lot of variants. So it's easily that the grid integration testing only for under voltage ride-through testing, well, in the area of a few thousand tests, and that we can. So no one of us is really able to handle all the parameters, all the programs, handle this manually, and that in the end, after half a year, everyone is aware, okay, what tests do we have executed at 11:13 on this day. So what we're doing, we have this specifications with our partners and customers, and then we enter this and we call it then processable specifications, so that we can have an automated read of it. We normally do it in Python, stored in a database, and then we call it test automation. We have here a simplified graphical user interface, and this is then where we can see, okay, we want to do this and this test, and this will get the information from the database. And then, of course, we are creating the test report on, we're getting all the information, what tests should be done with which parameters will be inside the test report. But this is then to enable really the benefits of the test bench, and not showing that it's technically working. So, but to handle all this amount of tests, we need there a lot of efforts in the test automation. So I'm a little bit only 10 minutes left. Some words on our grid emulator. So we have here a very special approach. We are running here our inverters, medium voltage inverters, as a single phase, as 3 single phase inverters. And these are then synchronized only by software. And this provides us the benefits that we have really an individual control of each phase, and there's no interaction. There are no interactions between the phases. And in some key factors here, we have different voltage level in 10, 20, and 30 and 36 kV. There's a low THD or the FAT, so under and over voltage functionalities from 0 to 130%. We have here a frequency range, what we can emulate with the grid emulators, and one important point is this impedance control for the container emulation. And this is also what Christian had in his presentation. This is the way how tests are done in the field. And there's one special thing, and this is this impedances. And we have here impedance. This is a series impedance that all the grid faults would be connected, produced by this short circuit impedance will not be seen by the overall grid. But this has a huge impact on the testing. And we try to emulate this by emulation of our voltage sec container. And and what we're doing here, we are building here an equivalent impedance, and we change this impedance. Then dynamically, and the whole thing is working. What you can see here, this is in orange. This is the voltage what is dropping over this virtual impedance. So in case, the mouse is so slow. In case of the series impedance is connected, we are having a huge voltage which will be dropped over this virtual impedance. In case of the failure, we have here a high current but a less emulated voltage. And in case of, again, the series inductance were disconnected in the post-fault time, we emulate a high voltage. So, and this is working. Of course, we can improve it step by step, but this is the approach what we are going to emulate also the grid behavior, or in this case, the low voltage ride-through container. And this more or less what's inside the standard, but you've heard it also from Aris. A lot of things are cropping up, and then it's very often under the topic of grid forming control, or you hear it in the area of grid forming control, that in this high penetration of power electronic interface power sources, this is HPU pipes, abbreviation, what is normally used. They're cropping up a lot of new problems what are not covered by the measurement standards and 61400-21-1, and they are maybe somebody we discussed it in the -4 committee, but they are at the moment under development. This is some issues with grid forming control. And Christian has also mentioned, okay, how can we deal with these huge wind turbines and in the power range of 50 megawatt and more? There are a lot of open questions how to deal. And yeah, we have to find here, also from the testing side, we have to find new answers, because implementing a European-wide grid forming control in all the power grids without valid testing methods, no TSO will allow this. So there's a huge pressure also in the testing area to improve our functions. And of course here, further reduction, further time to market, this is always a topic, but more or less this is a driver, not a technical issue. And there's one more thing, and this is what is the future of the power grids. And I think it was in the morning, it was described by Giles Dixon from that there will be all the HVDC connections. And there's one EU regulation from 2016, and this is that this is here. This is a sub name. This is a putting requirements on grid forming HVDC substations and how to deal with them. It's here really described, and there's one central issue, and this is that should be approved. There are no mutual interaction between systems, and now there's a huge drawback, and this is if they are in close relation under electrical point of views. So this is definitely something, if there are coming more and more HVDC lines in the power grid, that also wind turbines have to prove that there are no interaction with the HVDC things. And taking a look here to what is planned in Germany and what is ongoing. There are a lot of HVDC lines coming here in the northwest of Germany. Yeah, so some HVDC lines coming in here to Hamburg and also from the Baltic Sea. But there are also coming Ultranet from the south of Germany, developed by Amprion. There's Südostlink, there's Südlink, which is coming, what's built by TenneT and going from somewhere in Bavaria. Here also this is in Brunsbüttel area. And there's the Südostlink, which is then will be placed in Magdeburg. So from electrical point of view, complete north of Germany will be inside these rules. Then we have to see how to prove that there are no mutual interactions. And of course, we have here, this is on the big scale, we have also new challenges cropping up by how to operate and how to run wind farms at HVDC systems. So here's also the words from Ares. We have a really small short circuit ratio, how to deal with. There are new failure types what's cropping up. What is here shown, this is in case of an HVDC blocking, that there are some resonances inside the grid are excited, and we have in some way, we have to prove that the wind turbines will not totally be damaged or can really handle this. And there is one more point, and this is was also mentioned in the presentation from Ares. In Germany, there's this new technical extension of the guideline 4131, and this is describing also some scenarios for grid forming control, test scenarios, and requirements for EMT models. And the EMT model requirements, this is really cropping up to this inter-vendor interoperability of huge power systems. So wind farms on HVDC, or HVDC, but also the wind farms can start interacting between each other based on the controllers. So, and this is how the test scenarios are looking like. There's a changeable impedance, which can be switched on, can be switched off from a strong grid to weak grid conditions. There's a current controlled power generation unit, which is also acting. And in this kind of scenario, no one will be starting to build up all this changeable impedance. So it's much more worse to do this and emulate this behavior with grid emulators to do also wind turbine testing, on test batches in the future. So nearly my last slide, and this is addressing, that we want also to bring down the testing on a smaller, on a component level. And when we do this testing on the component level, we have much advantages that we can overcome some technical issues with a huge test bench. We can build up specialized test benches, creating our EMT models, and this is again our V model, but we will add a third leg here, which is describing all the models. So, and on the component level, we will do the validation. We will do the validation of the component and building up then our wind turbine model or the wind farm model with our EMT models, and then doing all the grid integration testing on the models. And this will provide a lot of more flexibility in testing, doing specialized test methods, doing tests in much earlier phase, and which are then also near to the design. This would allow a lot of benefits. yeah, and of course this is not only some ideas, we are having some new projects which are going to start then in the next few years. So Q4Wind, test bench, and mobile grid, but should not be the topic today. Yeah, thank you. Hopefully I'm in time.
Yes, that's okay. Thank you for your interesting technical talk, Torben. We are again open to questions. If so, to the audience, if you'd like to ask something, please put it in the Q&A section. I may start here, Torben. So we heard in the morning that the grids are changing, more hybrid parks are coming, different regulatory are there, and you described also some more changes to coming with HVDC systems. What do you think for these new technologies coming up? Do you think there's a different need, or do we need different technologies or develop new technologies for testing those electrical systems to meet those future requirements?
Sorry, I do not get it completely, but of course there are, we need here some, we have one huge drawback with the actual generation of grid emulators, and they are built on medium voltage technology, and this medium voltage technology is normally has an inherent very slow switching frequencies. So therefore, our controllability of the grid emulators has drawbacks. And to enable some really good power hardware in the loop functionalities, we definitely need here some more development in our grid emulators. This is for more or less only for the control functionalities, like this weak grid conditions, what we want to do. But they are also a little bit on the horizon. There will be new trend to introduce medium voltage technology more and more in the wind turbines. And then, of course, we have also some more and more challenges to handle the higher voltages in our specialized test benches. So there will be in the future, or there must be a further development of all the grid emulators and the testing equipment.
Okay, thank you. Due to the time, I will now wrap this session up. So thank you again, Torben, for your interesting slides. So this morning we touched a lot of different topics. We started with the strategy of the European Union. We had a view to the regulations in Europe and different countries, industry perspective and business view on grid forming, trends in grid integration, and the necessities for testing. Last presentation with a more technical view on testing and trends and what's going to change in grids. So to all those speakers, all of you, thank you very much for taking part, participating in this conference. Thank you to the audience for lots of interesting questions. The next point of the agenda is a lunch break. And we will continue with the second block at 12 o'clock Greenwich time. If I'm correct there, yes. So that's a good lunch break, and Paul McKeever is gonna welcome you to the next session then. So
right. Okay, well, good afternoon, everybody. Hopefully you can all hear me. I'm guessing you can. So welcome once again to the afternoon session of Virtual Wind 3. So this session, the focus is on floating offshore wind. So we've got 3 interesting presentations coming up. I'll obviously introduce each speaker one by one. There's been a bit of a change to the first presentation. Originally, a colleague of mine, Robert Proskowitz, was planning to present dynamic cables, on dynamic cables, and I'm going to hand over to my colleague, Luke Ito, who's going to present to you the Floating Wind Centre of Excellence that we've recently set up at the Catapult. So just a bit about myself. I'm the head of electrical research at ORE Catapult. I've been with the Catapult and NORAC before that for about 15 years, just entering my 15th year now. And my background is electrical engineering. So certainly looking forward to presenting a bit about our dynamic cable activities this afternoon. Also, I wanted to do a quick bit of housekeeping. So during the presentations, if you were with us this morning, Christian was talking about the Q&A button at the bottom of your screen. So if you want to ask a question during any of the presentations, then please type that into the Q&A function, and we'll deal with those after each presentation slot. So without further ado, I'm just going to try and share my screen now. We can get the first presentation underway. Okay, so apologies to the audience for that. So hopefully you can all see it now on full screen. So I'm going to talk to you for the next 10 minutes about dynamic cabling and some of the challenges that are unique to floating offshore wind. So I'll give you a bit of background into cable failures and market trends in the offshore wind sector, a very brief overview of some of the research that we're doing at Catapult, and how that impacts on the prediction for dynamic cable fatigue life. And then I'm going to talk about how we're starting to use validation and a specific dynamic cable test rig. These slides were originally put together by a former colleague of mine, David Young, but obviously I'm going to present them today. So in terms of cable failures, for those of you who work in the industry, you're probably aware that cables cost quite a significant part of a wind farm's investment. And actually around 80% of insurance claims in the offshore wind industry are linked to cable failures. So it's a significant challenge as we build out our industry. The table in the top right shows some cable costs that were collected recently from various UK wind farms. Bottom left shows some of the failure rates based on AC current-based cables in European offshore wind farms. And quite often, cable failures, there are a number of reasons why cables fail, but one of them is due to the propagation of water trees in the cable insulation layer. And that can be accelerated by both electrical and mechanical stress. So when we think about we're moving from static cables to dynamic cables, that mechanically driven aspect is even more important and certainly needs further analysis. The other thing that's quite interesting from this slide is the second example in table 1 shows the Guernsey Jersey preemptive cable repair. So they actually tried to repair the cable before a cable failure occurred, and that resulted in a reduction in cost. So something to bear in mind about the potential power of predictive capability. In terms of cable trends in our sector, in terms of the AC static cables, the industry's recently moved from 33 to 66 kV cables, which is presented on the left of the slide there. So that helps with both cost and optimization. But whereas that's kind of a move from a known technology to another known technology, albeit slightly less mature, the challenge that we have for dynamic cables is quite different, because the UK, whilst it's a global leader, it only has 32 megawatts installed capacity, so very different to the gigawatts that we have in static-based cable offshore wind. And at the end of 2019, there was no specific dynamic export cable designs available. So we've got this potential peak in floating wind over the coming years, but maybe a less mature dynamic cable situation. So quite a challenge ahead of us. So one of the things we're doing at Catapult is we've been developing a dynamic cable model to try and predict some of the fatigue and the damage that the cable's likely to experience. So that model includes a global model, which is top left of the slide, where we can show along a cable length where the greatest forces we believe are going to be. We then combine that with a FEA, finite element analysis of the dynamic model. and that allows us to produce a time history of stresses. And then from that information, we can calculate damage in a given cable design or setup. Also incorporated into the model, we've got an electric field model aspect, and that is developed on the basis that the electric field, as we know, is greatly distorted and concentrated at the tip of a water tree, and that can lead to accelerated installation breakdown. So some of the early analysis we've done with that model is we've tried to predict the time to failure for a dynamic cable, but its fatigue life based on current technology, current known designs. And what we're seeing is that instead of a required 25 years of cable life, it's quite possible that those cables aren't going to last that long, and they're coming out about half of that lifetime at this moment in time. So the other thing we're doing is we're constantly evolving that model, and we're using our dynamic cable test rig to validate the results of that model. So this is a rig that we purchased about 2 years ago, and what we do here is we're using this rig to test new dynamic cable designs as well as proving out our dynamic cable model. The rig is actually capable of simultaneously stressing the cable both electrically and mechanically, and it's also capable of being submerged in seawater. So you've got 3 different conditions that are relevant to the cable being simulated at the same time. So we certainly see this as the future as dynamic cables and floating wind progresses. So in conclusion, as I've shown in the last few minutes, we've seen the cable market move to high voltage, but also the distinct need for dynamic cable designs for floating offshore wind. We also know from our experience with static cables that cable failures, if they can be predicted, you can make significant savings in repair costs. And we've also shown a model which we believe presents a methodology that can predict dynamic cable failure. What it also shows as well is the technology needs to improve in order to get to that expected 25 years service life. And that model, as the dynamic cable designs will be, are being applied to the dynamic cable test rig over the coming years to do that crucial validation part of the process. And then the other thing I've mentioned is a potential major bottleneck for the floating offshore wind rollout is the lack of dynamic cable export designs. So that needs to accelerate quite significantly as well. Okay, so that's the end of my brief presentation. What I'm going to do now is hand over to Luke so he can present his presentation, and then we'll take some Q&A at the end of both presentations.
Thanks, Paul.
So just so Luke, just before you start, I was just going to say, Luke Ito is a colleague of mine at ORE Catapult, and he works in the Operational Performance Directorate. And Luke is involved in the program development of our floating offshore wind centre of excellence. So over to you, Luke.
Thanks, Paul. So hi, everyone. Yeah, my name's Luke Ito. I work within the engineering team in the in the Operational Performance Directorate here at the Offshore Renewable Energy Catapult. And so, as Paul mentioned, I'm just going to give an introduction to the Floating Offshore Wind Centre of Excellence. This is a program that was launched earlier this year in 2020. Yeah, I just want to take this chance to provide you with an overview of our work to date. I'll be happy to take some questions at the end if there are any. Yeah, so the remit of the Floating Offshore Wind Centre of Excellence is primarily on the UK business case. We are focused on reducing the cost of floating wind to a commercial rate by the early 2030s. Now, clearly, there is a sort of huge global opportunity here with emerging markets in Japan, the USA, China, Taiwan, Korea, Norway, Spain, and Portugal. So our aim is ultimately for the UK to be able to seize the opportunity as an early mover within that market, in doing so to capitalize on the existing offshore renewable energy capabilities and supply chain. In terms of the UK focus, the Committee on Climate Change here has a target for us of 75 gigawatts of offshore wind by 2050. And we feel that floating offshore wind has a major role to play in that, particularly in Scottish waters and the southwest of England and Wales and a region known as the Celtic Sea. In our analysis here at the Catapult, we believe that the floating offshore wind sector would represent a high return on investment in the UK. We think that it's a sector that can support up to 17,000 jobs and provide up to 33.6 billion of total gross value added to the UK economy, which we believe would far outweigh the cost of providing support in the initial stages of development for the sector. So ultimately, the Centre of Excellence is the primary aim is accelerating the commercialisation of floating wind in the UK and driving its role in delivering net zero and supporting economic growth here in the UK, particularly in the local economies. It's a collaborative, at the core of the Centre of Excellence is a joint industry programme model. So our core partners are industry bodies on the project development side. So you can see the key names listed on the right-hand side there, and there are potential new additions to be announced in the near future as well. But whilst our core partners are on the project development side of the sector, we also do engage with various other key stakeholders in the industry, be it industrial on the technology development side, or in academia, or in the supply chain. So our focus at the moment is on developing and going into the delivery phase of a portfolio of collaborative project activities across 4 key work streams. So these are outlined here. These can be summarized as technical development, supply chain operations, development consent, and delivering net zero. So just moving over to the next slide to elaborate on that a bit more. So the core of our program is the delivery of a program of core work projects, which are funded by this core budget, which is ultimately provided by the subscription fees of the industry partners. That said, we do have a flexible model that allows for a delivery of a range of project approaches. So, you know, for example, we could have, in addition to the core projects that involve the participation of all of our industry partners, there is the option for additional, as we term, discretionary projects that allow for the participation of third parties or perhaps a smaller number of the industry partners. So there is that flexibility there if there are external third parties who are interested in our activity and wish to collaborate in some form. But this general kind of project delivery model is underpinned by a range of activities that the Catapult delivers on behalf of the Centre of Excellence industry partners. So this includes stakeholder engagement. We've got a range of forums at the moment that we've established. So in terms of academic engagement, we've signed a collaboration agreement with the Supergen Offshore Renewable Energy Hub here in the UK. And through that agreement, we'll be looking to co-fund a number of new cross-industry and academic research projects looking at floating wind. And that's something that we'll be looking to kick off this year, in fact, through the Supergen's flexible funding call. So there will probably be some announcements within the calendar year regarding that. But beyond academia, we have a number of forums relating to different parts of the industry. So in terms of the substructure developer community, we've got a forum that enables us to directly engage with substructure technology developers and provides that kind of window of opportunity for collaborative project activity in the future with those companies. And we also have supply chain forums as well, so that we're doing as much as we can to maintain engagement with the various key aspects of the sector. Beyond, and just beyond the stakeholder engagement, there's a kind of additional enabling activities that we're kind of undertaking to sort of support that project activity work. We've developed and maintain a number of databases that kind of inform the project work going forward. So these relate to databases on industrial R&D activity related to floating wind around the globe, as well as a database on the UK supply chain, a geospatial database which underpins our kind of deployment modeling for floating wind, as well as detailed databases of all of the floating substructure designs that we're aware of. Perhaps also worth just drawing attention to one or two of the other activities, such as innovation challenges, which are more of a one-to-one type model of project delivery. So these are something that we run on behalf of the partners. If any one given partner has a particular technical challenge that they would like to engage with the supply chain in a secure manner with, in order to identify a solution, the Innovation Challenge program is something that we offer on behalf of them in order to address that need. So just in terms of the kind of prime areas of focus, at the outset of the program, we undertook an initial engagement exercise with our industry partners to establish where our primary areas of interest lie. And these have kind of resulted in the sort of 10 key areas that you can see on the screen at the moment. So just to touch on a few of those in a little bit of detail. Also the issue of the development and consent of future floating wind farms in the UK is a question that the project developers are keenly focused on at the moment, whether there are risks in the development process specific to floating wind that we need to identify and mitigate, or indeed whether there are opportunities for the development process for floating wind to be made more efficient while still maintaining the kind of required level of rigor and diligence expected of the consenting process. Obviously, supply chain capability and capacity is a primary priority for us, and extending that to port side capabilities and infrastructural capabilities as well, in order to deliver large-scale pipelines of floating wind projects in the next decade. We will need to fully understand in as much detail as possible what the current capabilities are and where the investment requirements lie going forward, so that our supply chain can deliver the services required of our project developers in the UK. Also cost modeling and understanding the commercial drivers for floating wind. Naturally, each company will have its own understanding of this, but for the Centre of Excellence projects, we want to have a cost modeling stream of activity that underpins all of those activities. And this is something that we have already kicked off, which I'll touch on in a little bit more detail shortly. Just before I move on, obviously mooring system design and dynamic cable system design for manufacture and assembly, that's a key area of interest. O&M strategies for floating, major questions such as in-situ repairs versus tow to port repair still remain generally unanswered for the sector. Heavy component exchange as well from floating platform to floating platform. There are a number of challenges that will need to be addressed in the coming decade. in order for commercial deployment to be achievable. So in terms of how we've converted some of these areas of interest into initial project activity, you can see across the top of the slide there, the 4 general work streams that I mentioned earlier. So just to draw your attention initially to the 4 projects in blue, these were actually co-funded between the ORE Catapult and the Scottish Government prior to the official launch of the Centre of Excellence. And these were ultimately a collection of desk-based feasibility studies that we undertook so that we could inform some of our activities going forward into the Floating Wind Centre of Excellence proper. So the areas that we focused on in these feasibility studies include floating substructures and the ability of the Scottish supply chain to assemble or fabricate these in the near future. Obviously, a mapping exercise of the existing floating wind supply chain, techno-economic analysis of the potential for hybrid bottom fixed and floating offshore wind sites going forward, and whether that's an initial commercial opportunity for the sector. We also looked into synergies for Scottish aquaculture and floating wind, whether there is an opportunity for co-location, and what that might require or even look like. Again, in terms of potential initial commercial opportunities, we did a study looking at the potential for offshore oil and gas assets to be electrified using floating offshore wind. And this has actually kind of triggered some further work with the Oil and Gas Technology Centre, exploring this in a bit more detail. And also we looked at a study exploring the requirements for offshore wind grid connections in Scotland. So that was fixed bottom and floating, but again, that's kind of informs some of our grid modelling work going forward. So those projects predate Just, but going forward, following the official launch, we've launched 4 initial kickoff projects. So these include a project looking at the development and consenting process for floating wind and where the risks and opportunities lie. So this has just been kicked off actually, and it's a project that involves outlining the development and consenting process in the UK for floating wind, and exploring the nuances in the various devolved regions, including England, Wales, Scotland, and Northern Ireland, and basically pinpointing where the current areas of risks lie in the process, and outlining mitigative actions that the Centre of Excellence can take in order to address those risks, and equally identifying the areas of opportunity to develop the processes as outlined. So they can be ultimately made quicker and more efficient, whilst being as thorough as required. Within the technical development workstream, we have a very similar project in structure to the development and consenting process, but this time looking at the certification, classification, and applications of standards for floating wind. Again, the process here involves outlining the key standards relevant to the entire life cycle of a floating wind farm, from development, design, manufacture, and assembly, right through to installation, operation, maintenance, and decommissioning. And again, identifying where the areas of risks lie in that, and understanding what mitigative actions we can take, and also whether there are opportunities, perhaps in terms of where the current standards that are being applied are overly conservative, perhaps if they've been transferred from the oil and gas sector, for example, and if there are opportunities for those to be developed to a more appropriate and proportional standard for the floating wind sector. Also within that technical development workstream, we've got a project that we've actually just completed looking at cost reduction pathways to subsidy free for the floating offshore wind sector. This particular project was delivered by the ORE Catapult on behalf of the Centre of Excellence partners. So the process behind this involved outlining the key components of floating offshore wind, levelized cost of electricity at the outset, And then we undertook a deployment modeling exercise based on GIS modeling, so that we can understand where the likely areas of deployment might be for floating wind based on the kind of the physical parameters. And once that was understood, we then undertook a cost modeling exercise so that we could understand where the potential for cost reduction lies for floating wind, based on technology innovation and learning rates, the scale and rate of deployment over the course of the next decade and towards 2050, as well as the effects of supply and demand and reduction in risk. So as I said, that project has just been completed, and we'll be looking to make some of its findings publicly available in the very near future. The fourth of the kind of initial kickoff projects looks at the role of floating offshore wind in delivering net zero for the UK, and the kind of general benefits that it brings to the energy systems in the UK. So this particular project falls within the role in delivering net zero work stream. So I suppose through this one, the aim is to understand how the benefit in terms of greater geographical deployment of floating wind, i.e. being able to access deeper waters and the more diverse wind resource that results from that, how that converts into or translates into energy systems benefit for the country. This is something that we have the Met Office involved as the delivery partner in terms of providing the weather modelling, and also Imperial College London are providing the energy systems modelling. This is an area of expertise for them in particular. So in terms of those four projects that I outlined, the remaining three that are yet to be completed, we expect to be wrapped up by the end of the financial year, which is the end of March, all being well. And then looking forward, just to quickly touch upon some of the areas of project activity that we'll be looking at going forward. As I mentioned before, dynamic cabling and mooring systems, understanding efficiency of design from a manufacturing design for manufacturing assembly perspective. Those two projects will be kicking off shortly. We also have a project which is continuing the work that we've done in the initial supply chain mapping, and the aim here is to basically understand and specify the investment and infrastructural improvements required in order for our supply chain and infrastructure to be able to deliver large-scale pipelines of floating wind projects going forward. We also have a project looking at potential interactions between floating offshore wind sector and its future deployments and the fishing industry. So we've got, this is actually just being kicked off currently, and we have a range of stakeholders from the floating offshore wind sector and the fishing industry around the table, and we'll be hosting a series of workshops through this project to pinpoint exactly where the areas of interaction or impact might lie, whether that requires mitigative actions or there may even be development opportunities for us to work in those areas together. And the aim for this project is to set out a roadmap that will outline future relevant project activities that the Centre of Excellence or other partners could undertake going forward. And finally, an additional project looking at existing O&M modelling tools that exist. So we'll be running a benchmarking exercise for the currently available commercially available tools in O&M, understanding how applicable they are to floating wind. Many of them have been made available to the fixed bottom wind sector, but we're keen to understand how they can be transferred to handle some of the nuances with the floating offshore wind sector. Yeah, that concludes everything that I was hoping to get across. I appreciate it's quite a lot of information all at once, but hopefully it gives an indication of the areas in which we're working, and if there is something of interest for your own organisation, there's an opportunity for you to reach out to ourselves going forward, and we'll be happy to speak with you in the near future. Yep, unless there are any key questions, that's everything from me. Thanks very much.
Okay, thanks, Luke. Thanks for that presentation. I'm just looking in the Q&A box. I'll just start my video. Just looking in the Q&A box, there's a few questions related to cables, which I can take in a minute. I've got a couple of questions for you, actually, Luke, based on your presentation. So I'm just thinking in terms of, so you've presented there a number of industry and other stakeholders that are already signed up to the Centre of Excellence. What kind of opportunities are there for new entrants? Are you still taking new participants, and how would they go about getting involved?
Yes, the answer is yes. So in terms of kind of core partners to the Centre of Excellence, we've limited core partners to project developer community, but there is still opportunity for companies involved in project development to join. We're expecting announcements in the coming weeks for new entries, all being well, and that still applies to those that haven't might not have engaged with us yet. Obviously, the current financial year is coming to a close, so it may well be that the new entrants will want to join on a subscription basis from the next financial year onwards. That said, there is still an opportunity to join this year and gain access to the initial outputs of the early project activity. But to other kind of organisations that don't fall within that kind of core project partner category, yep, absolutely. By all means, reach out. We have a range of kind of forums for various stakeholders. So it may well be that one of the existing forums will be relevant to your organisation. But if that's not the case, we're still very keen to have to engage with yourselves and see how we might work with you going forward. If the interest is more on a collaboration perspective in terms of engaging with some of our projects, as I said earlier, we do have a flexible delivery model that that allows for that. So that's certainly a conversation that we can have. So in summary, just please do feel free to reach out, and we will take it from there ultimately.
Yeah. Okay. So I think the key is, yeah, if you're interested in getting involved, then get in contact, and then you can discuss those flexible options.
Yeah.
Okay. The other question I was going to ask you was, in terms of the next sort of 12 months or so, what do you see the main research and innovation activities being in the program generally?
Yeah, no. So we'll be looking soon to develop the projects for the next financial year. So this does remain quite open at this stage. Some of it will naturally kind of follow on from the initial kickoff projects that we've had this year. But there's no real restrictions in terms of the areas that we expect to be working in going forward. Hopefully, through our collaboration with the SuperGen, we will see a bit of see some initial collaborative activity with the academic sector going into that year. But ultimately, it does remain quite open. Nothing has been confirmed as yet in terms of the specific projects that we'll be launching from April onwards. So the opportunities are quite open at this stage. Yeah.
So do you kind of foresee any, or do you predict any trends? Are you expecting a surge in mooring-based projects, dynamic cables, structural? What's the feel at the moment?
Yeah, I suppose that will ultimately depend on how the initial projects play out. As they could be kind of viewed as a sort of stage gate to the next set of projects. And also something that's worth mentioning is that we are in discussions with other comparable initiatives, such as the Floating Wind JIP through the Carbon Trust. So exactly how our future activities are shaped will depend on the outputs of our initial projects, but also being steered in order to try and avoid duplicating existing efforts in other programs. So yeah, I appreciate that's not a kind of direct or specific answer. It ultimately does remain quite open at this stage, going into that next year.
Yeah.
Yeah.
Okay. Yeah, no problem, Luke. And thanks for your time.
Thanks, Paul.
Okay, so I'm going to head back to the Q&A box and try and work through these questions. So we had a question from Bala Ramesh. So thanks for the question, Bala. And you were asking what software is used to predict the motions and dynamics. So that's obviously going back to the cables presentation that I gave earlier at the start of the session. And we're actually using ANSYS and ANSYS Maxwell for our simulations to date. Then I see we've had a few questions from Lawrence Farney. So I think, Lawrence, you've rephrased your question a little bit, actually. So I think there's two aspects to this. One of the things you asked was, is the lifetime versus water tree length graph simulated or based on test results? So it's more or less simulated. We do have some collaborations with cable manufacturers where we can get some real lifetime data, but certainly the test rig that I showed in the presentation is very early days, and what we plan to do is get more and more test rig results over the coming months and years, so that those kind of results are validated in effect, but they're certainly predominantly simulated at the moment. And then you asked a question about the graph showing the fatigue life, the time to failure, and you were asking a question around the constant aspect ratio. I must admit, I don't have a detailed answer for that, but essentially what we're doing with the model is we're starting with just a mechanical only simulation, then we're adding bits of modules that we've got in the module to it, and until we get to a quite comprehensive combination of factors that go into it. What I can do, Lawrence, is if you want me to ask one of my colleagues who actually uses the model, I'm quite happy to take that question away and give you a more detailed answer. And then we had a couple of questions from Mazhar Ali. So thanks, Mazhar, for your questions as well. So you were asking about how do you cope with the loads applied due to turbine movement during installation or connections? Do you already get an estimate of stresses or loads for a particular site? Essentially, our model, we haven't done any specific installation or connection type simulation yet, but you're kind of implying how we would do it. We would normally get an estimate of stresses or loads, as you say, and that's very much site specific, and that can be plugged into the model. So if you wanted to simulate the actual installation process or the cable connection process, we could do that with the model. And as you quite rightly point out, it's not just the movement of the turbine, it's the sea state as well. So there's other factors in there. And then you also ask about, Mazhar, you also gave me a question about the statistics. Around 10 incidents of cable failures are reported with an average downtime of 100 days until 2017. And you're asking whether I thought the design strategies have been revised in the last 3 years. Well, certainly the sector as a whole has matured a lot in recent times, and a lot of that is kind of learning by doing. So if you talk to the cable designers and the cable installers, they're just much better at installing cables and knowing what works and what doesn't work. I haven't got any specific innovations because you would probably need to talk to the cable designers and installers, but certainly we're certainly in a much better place than we were even a few years ago. And it's also worth pointing out that a big number of cable failures can happen during the installation phase. So if the installation process is improved and matured, then that's going to have a significant impact on cable failures. Okay. I think I've got time for one more question, and then I'm going to hand over to our next speaker. So, got a question from Chris Gotts from the University of Southampton. So, Chris, you're saying you're interested in more information on the dynamic cable models and results. Certainly, the presentation slides will be publicly available, so you can certainly look into that. And also, in addition to that, I'm sure that we'd be happy to talk to you offline if you wanted to ask some more questions. Okay, so right now I'm going to hand over to our next speaker. So our next speaker is John Tanday from SINTEF. So I know John very well through his work in the European Energy Research Alliance and European Technology and Innovation Platform. So we're both advisory board and management board members of those organizations. So as it says on the slide there, John, in 2019, May 2019, he was awarded the Mission Innovation Champion for his research achievements in offshore wind. And in his number of years working for SINTEF, he's certainly well known for his work in the Noitec Research Centre. And as it says there, it generated 40 innovations with a potential net present value of around 5,000 million euros. So significant amount of money. So I would certainly say that John is more than capable of talking about the next topic, which is all about the SETwind Lighthouse initiatives in the European programme. So over to you, John. Welcome.
Thank you. So I will share my screen, I guess. And exactly where is that one?
So it's the green share screen button along the bottom of the Zoom.
There it is. Thank you. And I'm trying to, yes. I hope you see my screen all right. And I'm happy that you're listening to my presentation. I'm going to talk now about the SETwind Lighthouse initiative. And the SETwind is a European project that is coordinated by DTU in Denmark. I'll explain a little bit more about that on the next slide. You can see the partners from the project here also. And I will also explain what we mean with the Lighthouse project. So SETwind is essentially a project that started in 2019, funded by the European Commission. It will last until April 2022. And it is a project to support the implementation of the SET plan for offshore wind energy. And the SET plan is the strategic energy technology plan. And that's the European Commission's plan for how to implement renewable energy technologies to reach climate goals. And then the SETwind is particularly then supporting the activities on offshore wind. So as part of this activity, we are developing a basis to have a lighthouse project, 1 or 2 lighthouse projects on offshore wind. And what we mean by lighthouse projects in this context is large European research projects that will address the grand scientific and technical challenges that are crucial for the further advancement of offshore wind energy, providing new knowledge and basis for innovation. And this is an initiative in development by the SETWIN project. It means we are not addressing a specific call at the moment. We are not actually developing the project. It's more about building the basis for having a European call to address these topics. And I'll explain to you later on now during my presentation why we think this is important. So, first of all, offshore wind is a great source of energy. It has the potential to deliver 18 times the global electricity demand of 2017. This is according to an IEA study that was published, I think, last year. It's quite detailed study. It looks into the wind resources globally and consider the available wind resource at a certain distance from shore and at a certain water depth and so on. And quite detailed. Then you have the European Commission scenario to reach climate goals. The most ambitious scenario is to install 450 gigawatt offshore wind by 2050. This would supply 30% of the electricity demand in Europe by 2050. This is, more than 20 times more offshore wind capacity than we have today. So it's a huge offshore wind development that the European Commission is foreseeing here. Equinor and Ørsted, as main developers of offshore wind, they have suggested that globally offshore wind can supply or reach 1,400 gigawatts by 2050, so 3 times the European scenario, and this sounds reasonable in that context. Still, it's really, really big compared to that. Presently, the offshore wind capacity is 20-some gigawatts. Then it's so that 80% of the global offshore wind resource is over deep water, meaning water depths more than 60 meters. And when you go to these kind of water depths, you need floating wind to develop offshore wind at any reasonable cost. So developing offshore wind in this scale is of course the big opportunity for industrial development to create new jobs and value. And it is also a grand science and engineering challenge. So the vision for our work is offshore wind to be a cornerstone of the energy system of the future, meaning in 2050 that offshore wind will supply a substantial part of our electricity demand, maybe 30%, maybe more, but in that order. And to achieve this, we have defined 2 critical issues. One is quite obvious, and that is to enable reliable power system operation with such large-scale offshore wind participation. So if you're going to have a power system where you have 30% supply from offshore wind, and then the rest is supplied by land-based wind and PV and other sources of renewable energy not to emit any CO2, it's quite a different energy system from what we have today. And it is a very significant challenge to achieve the stable and reliable operation of the power system with such amount of large-scale offshore wind. And then this is, of course, a system challenge, but it's also a very specific large-scale offshore wind challenge in the sense that how to bring the offshore wind to shore, how to grid connect it, and how to operate the wind farms in a way that they can support the grid and provide stability rather than to disturb it. So that's the first challenge. It's maybe not so specific to to floating wind, but in part, I would say. The next one is very specifically on floating wind. And the challenge is quite straightforward. It is about making floating wind cost competitive. Today, floating wind costs maybe 3 times that of bottom fixed wind, so maybe 15 euro cents per kilowatt hour or in that range. Of course, the technology is very new. The supply chain is not developed, and also the technology is underdeveloped. And there is lots of opportunities to cut costs, and I believe it's reasonable to assume that we shall be able to achieve cost competitive floating wind already in maybe 10-15 years. And then for the next years until 2050, I think that floating wind not only can be cost competitive, but really the preferred option in terms of economics. So, how would we go about this? Maybe I go back a bit. If one asks sort of the normal engineers working within offshore wind, I think they would start talking about, okay, you need technology to change the blades while you have the floating turbine and you have a floating boat, and this is a difficult issue. You need to improve the floaters, you need to improve the mooring system, there's lots of sort of technology improvements. And this is very much true. And then these kind of improvements, they are very much also a question about engineering and sort of gradual development of technology. And this is, of course, extremely important. What we envision in the SETWIN project to be a lighthouse project is obviously also going to address things like this, but we will take a slightly more basic research approach. And the reasoning behind this is that although we have been working with wind energy for since the 70s, so for 50 years almost, we still don't fully understand the atmospheric flow physics inside a wind power plant. That's one of the grand scientific challenges that was outlined in the recent article in Science. We also have difficulties in understanding the interaction between aerodynamics, structural dynamics, electrical dynamics, and offshore wind hydrodynamics, not only in enlarged wind turbines, but also in very big wind farms. We simply do not have the tools to really fully understand this. And then thirdly, a grand challenge being pointed out in this Science article is the system in Science for integration of wind power plants into the future electricity grid to enable wind farms to operate and supply a large part of the electricity demand in the future. And by addressing these challenges, it's not just an academic exercise. It is actually quite important to be able to design better design tools, to develop better design tools. And if you have better design tools, you can design your constructions with less margins, you can use less steel, and you will save large costs. That's quite simple. Another thing, if you understand better the wind power plant flow physics, you can design your wind farms better so that they produce better and with lower structural loads So this is indeed not a question about doing an academic exercise just to figure out how things works and to understand the physics. It's actually also very much to help the industry making floating wind cost competitive. This is a quite simple hypothesis, but I think it's still okay to state. And what I think is that in order to succeed in bringing floating wind towards its full potential, to reduce the cost, to be cost competitive and so on, you need to take an interdisciplinary research approach. And you need to consider not just the wind power plant or the blades or the substructure or the tower or the generator by itself, but you need to consider it together with the surrounding nature, the wind, the water, the soil, everything, and the electric grid, and to be part of the same system and to understand the complex interactions of all these parts in all its details. So it's not about making a very simplified sort of overview assessment, but really to understand all the complex interactions in all detail and put them all together. Then we will succeed. And how do we do this? I call this the holy grail of data. And it's actually a paradox that we have all these wind farms in operation, and there are enormous amount of data available from these wind farms. But very little of these data are available for open research that can increase our understanding about how the flow physics inside the wind farm is, how to understand that, how to operate the wind farm more efficiently. We do not have an experimental facility that allows us to collect data in the level of detail that we like, and also to be able to share the data between researchers, to understand them and to criticize them and to figure out why things are like they are, and also to figure out how to best operate and design the future wind farms. When we talk with industry about this, the normal response is that yes, it's great, and we would be positive in sharing data, but of course there are some formalities. And then when you start digging into the formalities, it normally sort of boils down that you are able to get some data under strict confidentiality agreements, and it's very difficult to share, it's very difficult to publish, it's very difficult to do the normal things you do to bring research forward. And also, if you ask to do an experiment inside a commercially operated wind farm, that is very often not possible at all. One of the experiments we typically would like to do is to stop a few turbines and see the effect of how the flow is changed, or to alter the operation of a few wind turbines to see how the flow is changed and the loads and the production and so forth. And this is typically extremely complicated for a good reason. We are talking about huge valuable assets, and I quite understand the position of the professional actors in the wind business on this. So my vision would be to have instead a small-scale wind farm dedicated for research. And this small-scale wind farm should be with lots of turbines, like shown on on the slide here, maybe 50 turbines, maybe 100 turbines, something like that. And it should be, but it should be small turbines so that it would be for research purposes. And I think we could get good results even deploying wind turbines with sort of 2-meter diameter rotors. If the terrain is flat, if it is on a flat landscape, you would still have relevant flow variations inside a wind farm, and you could still operate the wind turbines with variable pitch and variable speed, so you can operate them and do all the studies you like, but in a small laboratory environment. And this is the same we do with testing in wind tunnels. Only then we test 1 or 2 turbines at the same time, or we test them very, very small, and then you lose a lot of the effects you would like to see. Or when you test things in an ocean basin lab and so on, you also test it in scale. So this would be a scale 1 to 100 or 1 to 50 or something, which is, I think, a quite relevant laboratory scale. And it would be then a source of open data. So if we succeed with this, what we like to see is that the European Commission comes up with a research and innovation a call in an upcoming Horizon Europe program. And we would like to see 100% funding from the European Commission for this research and innovation action. But of course, enhanced through coordination with national projects. And we would like to see 1 or 2 projects that address a minimum 2 out of 3 of the grand research challenges. So these are the improved understanding of the flow physics, the dynamic interaction of enlarged turbines, and the system science for integration of wind power. And I would suggest that the call asks that an interdisciplinary approach should be taken. I think that's essential. And of course also that the researcher work closely with the industry, so to make sure that the new knowledge that is generated is relevant and is transferred to the industry and is also giving a basis for innovation. And to put numbers on this, we are considering projects to address this to be in the order of magnitudes of some tens of millions of euros and lasting for some 4 or 5 years, and would include strong research groups from all over Europe to work together in this interdisciplinary approach. So, why is this interesting for the European Commission and the industry? Well, we believe that knowledge plus industry is valuable. So simply from the academic side, from the research side, to developing this and assessing this or addressing these grand science challenges will bring new knowledge that can be applied by the industry to give valuable innovations and savings in cost of energy for floating wind. And in the previous research I've done in Novitec that Paul was so kind to mention, we assessed the value of the innovations, and I'll just show a short movie here to explain a bit about that. I'm not sure if you hear the music, but it's pling plong music, so I don't think you need to hear that, but I can just talk you through it. So from the 40 innovations, we'll just show a few examples that generated this value, 100 times the total budget of the center. So one is on electric losses, one is on robotized inspection system, optimizing operational maintenance, coatings, and design software tools for design offshore wind turbines. So research pays off. If you, well, maybe you can do this even without a live audience. You can just answer by the chat. So my quiz to you is: which of these 8 innovations do you think paid off the most? And this is not according to our calculations, but by independent consultant that looked into our innovations and sort of did a calculation. If these were implemented and used by the industry, how much would they value? So which of these 8 innovations had the highest value? And yeah, this is also check if you remember them. I will tell you afterwards anyhow. Okay. So summing up, the 2 Lighthouse initiatives, I think, represent great opportunities for new industry, employment, innovation, and an efficient carbon-free power system. There is a well-established need for more research, innovation, and deployment. This is documented by the ERA JP Wind Research and Innovation Strategy. It's documented by other research and innovation strategies by the European Technology and Innovation Platform for Wind and by the European Academy for Wind, and also by this science article that I quoted earlier on. So bringing the Lighthouse initiatives forward as large visionary research projects to solve the grand scientific and technical challenges, I believe will provide a solid foundation for the successful advancement of offshore wind to be a cornerstone of the energy system. Thank you. Now I'll stop sharing, I guess, and I'm happy to take questions.
Okay, thanks, John. That was a really interesting presentation. I'm just looking at the Q&A actually, and I don't think we've got anything specific yet for your presentation, other than choices of which innovation saved the most money.
Yeah.
So I'm sure you'll tell us eventually. Actually, whilst we're waiting for a few more questions, I've got a couple of questions that I've written down myself. So you mentioned that the 2 big Lighthouse initiatives. So it's obviously number 2 was floating offshore wind, and number 1 was, I guess, electrical infrastructure. And I'm just wondering whether you could comment on the dependency of those on one another, and how one can potentially enable the other. And what I'm thinking of is, floating wind, as it really develops, you're going to go into deeper and deeper water. You're going to be further offshore, which puts different constraints or different requirements on the electrical infrastructure.
Absolutely. Yes, absolutely. So of course it's difficult to predict the future, but if we look on sort of the big picture and assuming that there will be developed a lot of offshore wind in the future, if it's 450 gigawatt in Europe or 300 or 600, I don't know, but I think it will be large. And I think that's a general consensus in the industry that this will be big. And then considering that the most of the offshore wind resource is at deep water, it is quite reasonable to assume that a large portion of this will be floating. And exactly how large will depend on public acceptance on building offshore wind at bottom fixed locations. We haven't seen really the sort of public opinion on offshore wind so strong as we have seen on land-based still, but I'm expecting that it will not be so easy to develop offshore wind as it has been for the last few years in the future. So you will be forced to go further out from the shore, further out in the sea, and at deeper water. And then at the same time, as we make floating wind more and more cost competitive, and maybe the economic option at the end, I believe it's reasonable to assume that you will have a large portion of floating wind far offshore. And then to your question, Paul, well, it's far offshore and you have to bring the power to shore. And grid connecting far offshore wind farms haven't been done so far. We have built a few, or the industry have built a few demonstration wind farms being floating, but these have been quite near shore, some 10 kilometers or something from shore, so it's quite easy to connect to the grid. There has not been any large substation, for instance, so one need to develop technology to have large substations for floating wind. Should they be floating or should they be subsea? That's a relevant question. And then if you are able to develop this subsea technology for floating wind, could it also be not only the substation but also HVDC connections made subsea? So that's also quite a challenge. And when you're subsea, then it opens up an opportunity to say, well, maybe we should put pumped hydro storage at the seabed as well. And then you have a combination that is sort of helping the integration of large-scale wind to combine the floating wind with storage. Or you could envision sometime in the future just to have floating wind farms somewhere where it's tremendously good wind resources, but really off-grid, and you just produce hydrogen in an isolated system, and you have boats coming to pick up the hydrogen or ammonia or whatever you choose to be the end product of your energy production. So there are lots of opportunities, and there is indeed some interlink between these two sort of projects.
Yeah, I think what I'm hearing, John, is that it's likely that innovation and the development of floating wind technology will then drive the need for electrical infrastructure technology rather than the other way around. Rather than electrical infrastructure advancements, almost like enabling cost-effective locations for floating wind. That's my sense of things at the moment. Anyway, maybe it will be the other way around, but I don't sense that at the moment. Okay, right. The other question I was going to ask you was about you mentioned the small-scale wind farm idea. So I think you were talking there about turbines in the hundreds of kilowatts kind of level.
Oh, actually smaller.
Right. Okay. So maybe tens of kilowatts. Okay. So I was just thinking, in terms of the location of that small-scale wind farm, does that particularly matter? Were you looking at a particular water depth there, or were you looking at completely controlled environment? What was your thought?
Yeah. To answer first your question about size, what we have been playing around with so far is actually to have turbines with 2-meter rotor diameter. So 2-meter rotor diameter, that's sort of, then we talk about half a kilowatt or a kilowatt size turbines. They're quite small. And the idea of having them so small is a matter of cost. If you start making them tens of kilowatts, then each turbine is starting to be, it's not something you can just pick up and carry and fix on another location and so on. And the question is, will you gain a better physical understanding of having these larger turbines, or is this 2-meter diameter turbines large enough to gather or to explain the physics that you want to observe? and we believe so. But I understand this is something that can be questioned, and and we are still sort of in the development of this. It would have been really nice to have had this in a totally controlled environment, like giga big wind tunnel. But again, this would then be hugely expensive. You would need something like 50 times 100 meter wind section times, I don't know, 10 meter high or something. So and it would be extremely expensive to operate. And what we consider rather is to put it in the open air at the site where you have good wind conditions, and you just measure the wind, and you take whatever wind you get, and you measure the wind, and then you can control the turbines, and you can do still controllable experiments. But of course you cannot really control the wind, but you can measure it, and that's good enough for a controlled experiment. It should be on a flat location. To study offshore, I'm not sure if I would start putting it at sea, because what you really like to understand first and foremost is the wind flow. And it's the wind flow, yes, it depends a bit on the location and so on, but to understand the basic physics phenomena, you can still have it on a land-based location. Again, this for simplicity. It's also so that wind and waves don't scale in the same manner. So you'd have a problem finding a location with good wind exposure and small enough waves. If you think about these 2 meter diameter wind turbines, so but of course you could think about putting them in a basin, land-based basin, open air, so you'd have some smaller waves. That could be a possibility. Again, these are things for thought.
Yeah. The other thing that comes to mind is how you would then convince industry to scale up and roll out any successful innovations. It's quite a big leap to go from that scale to an operational wind farm.
Yes, and this is the same with all kinds of scale experiments. In the ocean basin we are operating at SINTEF, we are testing turbines and offshore construction, normally in a scale of 1 to 50 or 1 to 100. That is sort of the scale we are testing it in. And it is sort of established standard that you do numerical simulations and studies. These, when you are sort of satisfied with them, then you do your lab scale experiment to verify that your calculations are correct, that you do in your numerical studies, and that builds confidence in the industry to say, well, then we can go to full scale. So but of course, when they go to full scale, they still realize, well, when they do it the first time, then it's the first time of the full scale. So that's also with caution, but it is quite standard to do this, and I don't understand why we shouldn't do it also with wind farms when we do it on other components. So I think that's should be quite straightforward to do, and also it will bring confidence to the industry, but of course it will never replace a full-scale installation, but it can give quite valuable insights.
Okay, right, thanks, John. So I've had a few questions come in, all from Bala Ramesh. So he was asking whether you were happy or interested in collaborating outside of Europe, with countries like India, who don't really have offshore wind yet.
Oh, we like to collaborate with everyone who is interested. So please take contact and we can talk.
Okay, there you go, Alice. So if you want to get in contact, and then also he was asking, he or she was asking about whether wave energy, whether you're looking into wave energy.
Yes, we do. Yes, we do. And of course, there's a lot of interest about wave energy also in Europe. And there are a few projects developed. And I think the European Commission is also having big plans in terms of how to develop wave energy. But this is outside my field of speciality. So it's better to talk with someone else about that.
Okay. And I guess you were also talking about potentially you could use power to X to basically take the energy stored back to shore. So the comment was that burning ammonia can emit some pretty nasty gases, NOx gases. So hydrogen is much better. Although I understand ammonia is easier to handle and transport. So certainly, I would imagine it's better from an environmental perspective. But there's other factors as well.
Yeah, I think the discussion about hydrogen, ammonia, or other fuels that you can produce from clean energy sources, that's not really a question for the wind energy experts. I mean, we as wind energy experts, we can provide some clean energy, and we can also provide some electrical engineering solutions to operate the system, to carry out electrolysis or other chemical processes to produce a fuel. And then exactly which fuel that should be, that I like to leave up to those that are experts in chemistry or how it's easy to transport and how it's easy to use and also emissions and so forth. I think the industry is still sort of trying to decide which horse to bet on, but hydrogen is gathering a lot of momentum these days.
Yeah, certainly in the UK, where I'm obviously based, there's a big push on hydrogen as opposed to other alternatives. Albeit, I think it's not. There's other factors as well, as I was saying, and I could certainly see a situation where even if hydrogen becomes a dominant choice, it might not be the choice for every single situation. So, okay. Right. I think that's all of the questions. So I guess, John, you've been keeping us waiting, haven't you, with your little quiz? So
So if you remember, there were 8 innovations, and they were including reducing cable losses, wind farm control systems, remote inspection systems, a new coating, optimized grid infrastructure, and offshore wind design tools. And actually, the 2 innovations that had the highest value to implement is the design tools. To improve the design of or to have improved tools to design offshore turbines and foundations. That was the innovations with the highest potential savings or earnings. Simply having more accurate calculations to understand the physics better. That gives a tremendous upscaling effect. When you start, okay, you can reduce the steel cost with 5%, and okay, remote inspection. Well, it's or better coating. It sounds really good. It is also very good, but the highest potential saving is actually from these design tools. and this is, I highlight this because it actually stresses the value of more basic research. Normally, when you think about innovation, you think about something, a new thingy that you will install or something. and that is good. It's perfect. It's a new product. I think it's really great, but one shouldn't underestimate the value of simply improving design tools. That is also having a very high value in terms of reducing cost of energy from offshore wind or increasing profits. And this study we did in Owitech showed that very clearly.
Okay, right. Well, thanks for that, John. And hopefully that was interesting to everyone. I'm sure it was. So thanks once again for your presentation.
Thank you.
And I think we're pretty much out of time, so we'll move on to our final presentation. So thanks, John. Thank you. Okay, so our final presenter is Dr. Marieke Leemester. I've hopefully pronounced that reasonably well. So she's a research associate at Fraunhofer IWES, and she's going to talk to us about experience in the design, optimization, and analysis of global system dynamics. So been a research associate since 2017 at Fraunhofer IWES, and then clearly got some interest in floating systems and this area of research, with references to her master's thesis and also her NGD thesis, which she recently defended, and that was based on reliability-based optimization of floating wind support structures. So without further ado, I'll hand over to you, Dr. Leemester. Thank you.
Sorry, we can't hear you. There's no sound coming through.
Can you hear me now?
Yep, that's you. Thank you.
Oh, sorry. I hope you can see my presentation. Thanks for the introduction. I want to give you some insight in the experience we have at Fraunhofer IWES in the analysis of global system dynamics of floating offshore wind turbines, as well as in design optimization. So it's kind of tackling the last point mentioned by John, that we are also doing modeling of the floating wind turbine systems, which is highly relevant. So I will start with the global system dynamics based on a research we are doing in an international EU project dealing with the floating offshore wind turbine demonstrator. So I will shortly present this project and as well as the activities we are dealing with. And then I will come to the point of optimization of floating offshore wind turbine systems, starting with a theory and modeling, and then presenting also some examples on design optimization. And in the end, I will conclude and give some outlook. So to start with the global system dynamics of floating offshore wind turbines, as I said, it's based on a project Fraunhofer IWES is involved in. It's AFFLOAT. It's short for Accelerating Market Uptake of Floating Offshore Wind Technology. And it's an Interreg Northwest Europe project, so covering the countries France, Ireland, Germany, the Netherlands, Britain, and I think I forgot someone, Belgium and Luxembourg. And the project started end of 2018 and is planned to last 4 years. And it's partially funded by ERDF. And the main motivation is to develop a high survivability, cost-competitive floating offshore wind turbine by having a demonstrator deployed off the west coast of Ireland. We are altogether 8 project partners coming from the Northwest Europe region. And as I mentioned, we plan to have a demonstrator of the west coast of Ireland. And here you can see the location. It's at the AMETS test site, so the Atlantic Marine Energy Test Site. And there we have 2 potential sites to investigate. So either site B, which is more close to the shore and only has 50-meter water depth, or we can also use site A, which is further offshore and already at 100-meter water depth. Why did we use this test site for deploying the demonstrator? Because as you can see here on the picture, it's a really strong weather conditions, what we experienced there. It's a high energy offshore site and located at deep water, which is very close to the shore, already deep water, as you can see on the white figure. Furthermore, this area has also some sandy seabed, which is suitable for the cable and the moorings. And as shown in the previous figure, we have very strong wave and wind activities. So if this demonstrator survives under this condition, you can establish it anywhere around the world. So just some examples, significant wave height could be up to 16.7 meter. The wind speeds given here are measured at 1 meter above sea level. So at hub height, you expect much higher wind speeds. And there was a measurement here in this picture shown for a wave height of up to 12 meter in 2013. So really strong weather conditions. And with which system do we want to work in this project? It has to be survivable in strong weather conditions, but also cost competitive to compete with the bottom fixed system designs. And we are working with the floater design solution from the project partner Saipem. And this is based on a semi-submersible floater, which has tubular elements. And in total, you can categorize it as a pendulum stabilized floater. So you have this semi-submersible below the waterline, but at the top of the floater, and there you have connected with tendons a counterweight to add to the stability of the system. Furthermore, we only need some simple mooring lines due to the low motion response, even in extreme sea conditions. And also these catenary mooring lines require common drag anchors. We are using a lazy wave dynamic cable. And as we are using an existing onshore or also offshore wind turbine, but designed for bottom fixed systems, we need to adjust the control strategy, what Fraunhofer IWES is as well working on. So I want to go in some more detail on the specific systems of the floating structure. Just at first to give you some idea what numbers we are dealing with, what sizes we have. Here on the example of a 6 megawatt wind turbine with an exemplary hub height of about 100 meter. So with this wind turbine size, we would need to deploy the site A, which is further offshore and has a water depth of 100 meter. This would be sufficient for having a floating structure with a 6 megawatt wind turbine on top. And as you can see on the right, the semi-submersible itself would have an outer dimension of around 70 meters. Then to this structure, the counterweight is connected. This is just a circular steel bucket, and we are utilizing some heavy ballast material. This could be either magnet-dense or specific concrete with high density. And this steel bucket is connected with tendons, as said, to this tubular elements of the semi-submersible floater. Then, as well connected to the tubular elements, we have the mooring lines. We decided to go for 6 mooring lines. In general, 3 could be also sufficient, as the system is quite light because it's consisting out of single tubular elements. The system shows a little response in the extreme sea conditions. So therefore, we just require a very simple mooring line system with a chain diameter of around 84 millimeters, and the overall radius footprint would be around 550 meters. And in addition, there are some clamp weights included, and as mentioned at the beginning, we only need some common drag anchors. Now, how do we want to install this? The benefit of having this floating system is that on the one hand, you have the semi-submersible floater being assembled with a wind turbine on top directly at the harbor side. And at first, the counterweight is connected at the offshore side, and then the floating wind turbine system is towed above this counterweight, and you can use just common and proven offshore installation techniques. You don't need special ships. You just need normal tugboats and can install this floating wind turbine system. How far is this system already developed? The Saipem, the company, our project partner, has already performed some scale tests where you can see some pictures from on the screen. And the tests have been performed in Nantes, and then results showed that the system behaved better than expected, and that we can really expect that the system is behaving good in the strong sea conditions at the test site. And within this upload project, we are further defining the design, the final design of the floater. Fraunhofer IWES is therefore supporting with doing fully coupled system simulations and analysis, so that in the end we can improve the final design solution, which is then manufactured and put off the shore of the west coast of Ireland. And in the end, it's planned after the successful project of Afloat to have some commercial projects. And for this, it's also suitable that the floater design can be manufactured in series. So you have an on-ground assembly of the floater, starting with a vertical column and then the horizontal elements, welding the elements together, adding also the J-tubes and the ballast into the braces, doing also non-destructive testing. And this happens at the harbor side, and directly at the quay, you can place the wind turbine on top of the floater, because this combined system has a very low draft, and this is possible directly at the harbor. Another benefit with respect to the future development is looking at the trend of the wind turbines, which are increasing in power. The floater also can easily be upscaled, while the wind turbine will increase in hub height, tower length, tower mass, and RNA mass. The floater itself doesn't change that significantly. As you can see on the picture, the outer dimension of the semi-submersible remains nearly constant. Just the diameters maybe will increase a little bit, but the main difference will be that we need to increase the tender length as well as the amount of the ballast, so the amount and the size of the counterweight as well. But in general, this floating system design is fit for the next generation of wind turbines as well. In addition to this technology development, we also focus on floating offshore wind development plan. So looking further into the future, what will last after the project has ended. And therefore we are working together with some more partners, with some more associate partners, also coming from the region of Northwest Europe. And we have several aims for this floating offshore wind development plan. So we want to educate the investors and project developers that the floating offshore wind technology is already mature. And we also aim to have a coordinated change in the private sector perception of the floating offshore wind investability. And what's also really important is to create a supportive policy environment as well as an active supply chain, whereas we are focusing in this project on the Northwest Europe region. And these topics we have combined in 3 working groups. And within these working groups, we tackle the gaps existing and what plans need to be proposed. And in the end, out of the results, we will prepare such a floating offshore wind development plan. And we aim to have an agreed vision for the future floating offshore wind development to accelerate the market rollout of this technology. So that was more about the global system dynamics, because at that time we have an existing design solution. Fraunhofer IWES is doing a fully coupled system analysis. But beside of this project, Fraunhofer IWES is also working on optimization of floating offshore wind turbine systems. And at first, as I said, I will cover the theory of this optimization. We are working with Modelica library for wind turbines, short MOVIT. I think in the morning, Torben has also mentioned this, being coupled to some test simulations. And we are using this for modeling different wind turbine systems. The library is based on the modeling language Modelica, which is object-oriented and equation-based and has an hierarchical structure and multi-body approach. And as you can see on the right, in this figure, you can split up the very complex system of a floating offshore wind turbine into single components and further subcomponents. And this also makes it easy to exchange some components and represent different wind turbine systems, bottom fixed, onshore, offshore, or floating. So it's providing a high flexibility. And based on these component-based computational models, we can model any state-of-the-art wind turbine system and perform fully coupled aerohydroservoelastic simulations. And these we do with the help of Daimler in time domain simulation. And short simulation you can see on the right, just on the example of a semi-submersible floater with an operating wind turbine on top. Just to explain, the red dots are representing the mooring lines. It's just because of the representation in the model represented by single elements. This model created in MOVIT and also simulated in Daimler builds the basis for a framework we have developed for automated simulation. This framework is coded in Python. And at the beginning, the first step is to set up the interface between these three different tools. But there are some interfaces also existing in Python, and then it's relevant to define parameters which need to be accessible, which you want to maybe modify, especially when you are looking at optimization. Design variables are modified throughout the optimization process. And you also specify which wind turbine system models you want to simulate and under which conditions, how many simulations you want to perform. That's everything done in the processing of the model. Then in the next step, the single simulations need to be managed. And that's a huge benefit, especially for simulating several system analysis, for example, for design load case simulations, or also for doing optimization, that you can perform the simulations in parallel. So this you can specify here if you want to perform simulations after each other or in parallel. And in the end, you can execute the task and also get the outputs which you have specified before. And this framework for automated simulation gives the basis to the extension and integration of the optimization functionality. And this is done at the step when executing the task. You can integrate an optimization algorithm. You need to provide some additional information for specifying the optimization problem, meaning defining your design variables which you want to modify, setting some constraints, specifying the objective of your optimization. And then in addition, you also need to select an optimizer, and you can perform the iterative optimization. And in the end, based on your stop criterion, this stops the iterative optimization, and you have the outputs in the end again. So this framework for automated simulation and optimization we have applied to different optimization tasks, and two of them I want to present. First, an example for focusing on cost reduction, but also integrating some more advanced features. So the optimization problem uses the example of the OC3 phase 4 Sparboy floating wind turbine system, which has a 5 megawatt wind turbine on top. And I have specified an optimization problem with 7 design variables. On the right, you can see that I have subdivided the main column of the SPA into 3 elements, because the upper element should deal for gaining the buoyancy. The middle part should mainly deal for gaining distance between the first and the third element. And the bottom part is for being ballasted and therefore for obtaining a deep center of gravity. And then the 7th design variable is the ballast height itself. The ballast density is then a dependent variable, which is determined internally. Then the objective, as mentioned, it's focus on cost reduction. Therefore, the objective is to minimize the structure material volume. And there are some additional constraints for the allowable values for the design variables, but also for checking, for example, the wall thicknesses with respect to the diameters of the single columns, the allowable ballast density values, and further checks, for example, with respect to the draft of the entire floating system. The optimization approach followed some preceding simulation analysis for selecting one critical design load case, which is used throughout the optimization. The optimization itself is performed with a genetic algorithm. And due to the complexity of this optimization problem, I have performed more than 166 generations, and each generation contained 60 individuals. So this is due to the character of a genetic algorithm, which is mainly representing the law of evolution by Darwin. So you have single generations with individuals which are further developing. The result of this optimization is at first a reduction of the structure material volume by more than 31%, which gives a significant cost reduction and also an easier handling. As you can see, the wet shape is much more compact and not that long as this original spar. But it also includes and requires some advanced features. So I have considered some alternative ballast materials like Magna-Dense or high-density concrete, which are at the moment more and more investigated to be also used for the offshore wind industry. But if you look at this shape of the red line, at first it looks a little bit strange and you think this cannot be manufactured. There's a strong tail at the middle, but this requires some alternative manufacturing solutions. So this design solution is good with respect to hydrodynamics, but it cannot be manufactured by just welding cylindrical elements to each other. And you can avoid this constriction by using trusses or tendons for connecting the upper column with a large base column. And then if you consider such alternative manufacturing solutions, you realize that the optimum found shows some similarities to some most novel floater design solutions, as for example, the SteeStyle TetraSpar, or also the Saipem Hexafloat. So the second application example looks and addresses the future of the wind turbine technology development. So currently you can see a trend in the wind turbine technology going towards larger and larger megawatt class wind turbines. And this also requires the floater design process to come ahead and speed up. Because normally you have an existing design, you scale it up to a larger megawatt class, and then you need to optimize it again. And I aim to speed up this process by omitting this intermediate step of upscaling and doing it integrated in a direct optimization approach. So what I used was, again, this OC3 phase 4 spar buoy floating wind turbine system, which is for a 5 megawatt class wind turbine. And the aim is to obtain a floating support structure for a 7.5 megawatt wind turbine. And I used the reference wind turbine IWT by Fraunhofer IWES. And I implemented the floating system at first in MOVIT, as well as the larger wind turbine. And then I just needed to do some minor adjustments in the model for the spar buoy, for example, for matching the base diameter of the tower. I needed to increase the upper column diameter of the spar. And also I needed to adjust the ballast to make the entire system floating again. But these were just minor adjustments which were able based on hand calculations. And then I give this as input to the MOVIT Python framework and perform a normal optimization problem and iterative optimization algorithm. And in the end, I was able to obtain a floating support structure which is suitable for supporting this larger megawatt class wind turbine system. So to conclude, I started with presenting this AFLOAD project, where we are right now within the project on the way towards technology readiness level 7. The floating system design shows to be cost competitive and is quite lightweight. And it's also highly survivable in extreme environmental conditions. And additionally, the floating solution also is fit for larger wind turbines and for the future trend in the wind turbine technology. In the end, what we aim with this project is to show that the technology is mature and to obtain an agreed vision for the future floating offshore wind development. And the second topic I presented was the framework for automated simulation and optimization. And I have just presented 2 examples. So I also want to point out some other applications which we are at the moment already applying, or some future applications which we want to apply this framework on. So as it's also a framework for automated simulation, it's useful for performing a full set of design load case simulations, which commonly requires a large number of simulations. But you can also, for example, generate response amplitude operators in an automated manner, because these also require several simulations. And with respect to the functionality of using the framework also for optimization, you can, for example, use it for gaining a fast preliminary design and cost estimation directly at the beginning of the design planning stage, as the design doesn't need to be detailed at this stage, but the investors need to know about the cost estimation. Then, of course, you have also some design optimization applications with respect to single components of the system or the entire floating offshore wind turbine system. You can also address it for optimizing the controller strategy, for example. You can also include reliability aspects, which I have covered in my engineering doctorate studies. And as presented, you can also do some more future-oriented applications by including system scaling. And you can also apply optimization on a more broader view by focusing on the operational management of a floating of the floating wind turbines in a floating wind park. So I want to thank you for your attention, as well as for the funders. And just a short list of references what I used in my presentation, and I think I should be on time almost. And if there are any questions now, we should have still enough time for these.
Okay, thank you, Mariki. Okay, I think there's a few questions coming in. I'll just give the audience another couple of minutes. I've also got a couple of questions for you. The first one was you mentioned about the scalability, and you talked about next generation 15 megawatts. I'm thinking that Siemens Gamesa recently announced their 40 megawatt turbines. So I almost see 15 megawatts as kind of where we are now. So does it scale beyond that point? Have you considered 20 megawatts plus, or was that just an example?
It's just an example. I mentioned also the dimensions based on an 6 megawatt wind turbine. As it's just a demonstrator project, we don't aim to go beyond 6 megawatt. But I think the next step after this project could be a large step, and the 15 megawatt were just an example to show the difference in scaling up.
Yeah. Okay. So 20 megawatt wouldn't necessarily be a problem. It was, yeah, you just used a number. Okay. Mm-hmm. And then the other question I had was, do you think there's enough focus on the manufacturability of these designs as opposed to the hydrodynamic performance? Almost like, do you think there's enough focus on the MRL as well as the TRL? If that makes sense.
I'm not sure if I got your question right.
So in theory, you could design a floating platform that performs fantastically from a technical performance point of view, but it's almost impossible to manufacture. So do you think there's enough focus on the manufacturing side?
I think it's a question on how you approach this problem. Of course, you're limited in what you can manufacture, but you also aim for a good performance of the system. And I think from a modeling point of view, sometimes you need to make some simplifications because normally these people also don't know exactly all details of what can be manufactured and what not. But in the end, these designs should indicate in which direction manufacturing should go. But then it needs to be optimized again with respect to a manufacturing point of view. But it should represent nearly the same hydrodynamic response. So for example, if you have a really large diameter structure, you don't need to be able to manufacture, I don't know, 50-meter diameter structure, but you can realize the same response and performance of the system by placing, for example, smaller diameter structures in a circular manner around. Did it answer your question? Or?
Yeah, I think I guess what I'm getting at is that there needs to be sufficient consideration before it gets too late. You know, you can't just completely ignore, can I manufacture this, and get to the point where you've got a mature technology that doesn't make sense to build.
Yeah, but it's also important that you use manufacturing solutions which are feasible and which you can also apply for serial fabrication, because otherwise you cannot aim for cost competitiveness.
Yeah. Agreed, yeah. Okay, so we've got some questions on the Q&A. The first one was from Bala again. So the question was, how does the design perform when compared with a TLP, a tension leg platform, in terms of ease of installation and cost?
I guess this refers to the Hexafloat design in Afloat. So with respect to the performance, I would say it's quite close to a TLP. A TLP shows little motion response, and that's also what we see with the Hexafloat. But the installation is definitely more easy. The TLP has some limits with respect to the mooring system. You need to have really good soil conditions. You need to have special anchors which can be loaded in vertical direction. That's all what we don't need with the Hexafloat design, because we can use common catenary mooring lines and a very simple mooring system. The only thing is then the connection of the counterweight to the floating structure, but still, I think that's only with respect to the installation point where you can maybe also find some more improvements in the future, but I think it's more flexible as well as compared to an TLP.
Okay, thanks, Marike. The next question was from Lawrence Carney, and he was asking, is the pre-laid connector clump weight left on the seabed or suspended in the water column before the turbine is delivered?
It's first installed, and therefore either it's left on the seabed or yeah, I think it's first left on the seabed and then lifted up for installing the floating system. So that's the first step, installing the counterweight.
Okay. We have another question from Bala Ramesh. So the question is that the pendulum may dampen and decrease pitch and roll motions. What about heave and the possibility for slamming at high wave heights? And also, was nonlinear large amplitude equations of motions analyzed for the motions?
Okay, yes, so the pendulum system shows large damping in pitch and roll. We also had a test where it was not moored, so the system was still very stable. It was just because there was thrust, force, and wave loads, it was just constantly moving, but really good damping in pitch and roll. But heave is also not that significant because the structure is so invisible. You don't have a large surface in heave direction. So there are also no issues with the heave motion. What was the second question on nonlinear wave amplitudes? So based on the tests performed, there were no issues realized with strong motion response due to nonlinear large wave amplitudes.
Okay, I'll take your word for it. Okay, so we had another question from Lawrence, and it was related to the spar buoy. So the earlier question was on the hex flows. Did you say the genetically optimized spar design takes account of wave and current loading, and is it based on a typical site?
Yes, so in the modeling we have wave loads, current loads, wind loads, so a full aerohydroservoelastic dynamic simulation. And of course, it was a reference wind turbine system which was not installed or designed for a specific location, but still I have considered some representative environmental values for an area which is similar to where Hywind is installed. So in the North Sea region between Great Britain and Norway in this area. And yeah, then just following the recommendations by standards for different design load cases and extreme conditions as well, yes.
Okay, and then the last question we got was from Mazhar Ali, and the question was about what's special about lazy wave dynamic cable.
It's about the criticality of the strong motion of the power cable. So it's more that you have a lazy response of the power cable. You don't have to expect a severe motion response of the power cable.
Yeah, so I guess that reduces stress and fatigue.
Yes, that's the most critical factor for the power cable. Yeah.
Okay. Right, so I think that was all the questions, Marieke. So thanks very much for your presentation. And yes, I think thanks to all the questions from the audience as well. So yes, I guess we're pretty much out of time. I think we're due to wrap up about 2:15. So we'll. All I'd like to say is thanks very much to the 3 presenters this afternoon. Also, thanks to all of the organisers and presenters from this morning as well. And last but certainly not least, thanks to all the audience for participating, for listening to the presentations. Hopefully you've enjoyed it, and well, let's hope we've got another virtual wind event in the early part of 2021. Okay, so back to you, Vicky.
Thanks everyone. The slides and the recording will be available shortly. Thank you.